हो गया? A very good morning to all. I'm Dr. Swati Gupta, I'm Deputy Secretary in CBSC, and I welcome all the participants who have joined us through YouTube and Google Link for this training. Today, the topic of our training is air conditioning and refrigeration. This course is offered by CBSE at senior secondary level, and this course is actually created in such a manner that it will help teachers to explore different aspects of pedagogy and transferring of hands-on skills so as to develop a pool of skilled manpower for industries, also leading to their career growth and benefiting the society at large. Basically, it's about promoting holistic learning experience where students acquire specialized knowledge, skills, and develops attitude towards learning and contributing to the vocational ecosystem. It will be needless to say that this is what NEP 2020 has mandated, that children will be exposed to number of skill subjects from very early age so that they can understand the different subjects and learn lot of skills. So this subject can also help student to get acquainted to technical education from very beginning. So to understand more about this subject, I would now welcome our expert for today, Sir Bhola Pathak. He is Associate Professor in Mechanical Engineering Department of Pusa Institute of Technology at Delhi Skill and Entrepreneurship University, Pusa. He has done his Masters of Engineering from Delhi College of Engineering in Delhi University, and his specialization is thermal engineering, refrigerator and air conditioning engineering, and automobile engineering. He has over 25 years of experience in mechanical engineering. So, with this, now I request Sir Bolaji to please take over the platform and start with the training, please.
Thank you, madam. Is it shared now? Not yet.
Please go ahead with the screen share, sir.
ये शेयर हुआ, हमारा स्क्रीन शेयर हुआ कि नहीं अभी तक?
नहीं सर, अभी नहीं हुआ, अभी नहीं हुआ. प्रेजेंट नाउ का बटन होता है सर. हाँ, हो गया सर, आ गया.
Okay, thank you, madam, for giving me an opportunity to share my knowledge in this field with all the teachers. The teachers can they directly communicate with me or not?
Sir, the teachers will post their queries on the comment box of YouTube, which I will communicate with you because people are not allowed within the Gmeet.
Okay. Thank you. Thank you all the teachers on this training program. I am Bhola Pathak. I will be giving training theoretical aspect on refrigeration and air conditioning. So our topic of discussion will be history of refrigeration cycle we are using in this field, then cycle components, refrigerants we are using, air conditioning, psychometrics, and air handling unit if the time permits. Let us have the brief history of refrigeration. In 1823, Michael Faraday discovered a certain gas which can condense upon cooling at some constant pressure, and that cooling effect can be produced for creating the refrigerating effect. In 1834, Wright produced the ice by expansion of compressed gas. when we have the air, if we compress it and then we expand, the temperature of that lowers and the water particles will be produced. So that can be converted to ice, and that ice is utilized for other useful purposes for cooling of the space or substances. 1842, John Gorey used dripping ammonia. So cooling effect was generated with the help of ammonia gas. In 1858, Ferdinand Carey developed an ammonia mechanical refrigerator. So it was the first refrigerator based on the ammonia gas, and this was initially used for producing the ice for domestic as well as industrial applications. Then further in 1875, sulfur dioxide gas was used in those days for producing refrigerating effect. Then furthermore, 1881, rail cars were developed which was refrigerated. So likewise, there is a big history of refrigeration. When we come in the 19th century, it is the Will Carrier air conditioner we are using in our office or homes. So it was Will Carrier who designed the humidity control for air cooling system, and he developed a Carrier equation which was used further for designing the air conditioning system. In 1926, Savage Arms ice cream. This was the first ice cream unit was produced in the world. Now let us come to the 1929 onwards, 31 onwards. The modern refrigerant we are using, CFCs and HFCs, they were produced by in these years, and this development took place up to 1965. Then it was in 1939 that a compressor was developed for refrigeration system. In late 90s, 1974, the ozone theory was developed by Professor Raoul and Molina. And this ozone theory was a warning towards the scientific society that the refrigerant we are using, this is depleting the ozone layer in the stratosphere. And it was a great warning for the environmentalist. And ultimately, the effects of this ozone depletion has come on Antarctica. Many more, the scientific society, they got woken up and they took the many decisions to phase out the ODP, ozone depleting refrigerant from the industry, and so on. Many more protocols were, Montreal Protocol is one of the associative approach taken by the different 100 countries, including India. In 1997, the Kyoto Protocol intended to reduce the worldwide global warming gases. So many approaches have taken place to phase out the different fatal gases, which is very dangerous to the environment, and greenhouse gases, which is causing the global warming, the refrigerant which is causing the global warming. They were given warning to the industrialists to phase out in the phased manner so that the environment can be protected. With this background, we will come to the part one on the refrigeration system, that is the vapor compression refrigeration system. Let us start what actually the refrigeration is. In refrigeration, we simply transfer heat from the low temperature zone here by applying some appliances, that is the compressor, to the high temperature zone, that is the environment. So transfer of heat from the low temperature region to a higher temperature region with the help of some component at the expenditure of the energy is known as refrigeration. In refrigeration, we create in a confined space lower temperature than the surrounding. And for doing this, we apply a science theory, that is Clausius' statement of second law of thermodynamics. That is the main application of science in refrigeration technology. So the objective of refrigerator or refrigerating any refrigerating machine is to remove heat from a cold space and reject this heat to a hot space. So this in this figure you can see here is the space you want to refrigerate or maintain at a lower temperature than the environment. So from here the QL heat is taken up with the help of some work input, that is the compressor, and this is rejected in the atmosphere, that is the warm environment, atmospheric air. Here R indicates the refrigerating machine. The same refrigerator can be used for producing the heating effect also. So once we use for the heating purpose, then the nomenclature of this component is changed and we say that it is a heat pump. So both heat pump and refrigerator are the same component. Only difference is that application part. So in refrigeration, we produce the cooling effect, and in heat pump, we create the heating effect. When we are producing the refrigerating effect, here is the lower temperature. So there is chances that from the surrounding, heat will ingress into this space. So to restrict the heat ingress in the coldest room, we apply some insulating material. So these are the insulating materials, different, that may be the glass holes, then some files, then we have some puffs materials. So these are used for insulating the refrigerating machine. In refrigeration system, when you are cooling any space, so in that space there is chances that from the surrounding the heat will penetrate. So this heat penetration is known as the heat load, and this heat penetration can take place in different ways. That heat can leak into the refrigerated space directly from the atmosphere. In case your refrigerator is or your machine is exposed to that solar radiations or solar lights, so direct the solar heat will be entering into the space. If some products is kept in the refrigerated space, or human being is occupying that space like auditorium, cinema halls, hospitals, and so on. So even we produce the heat. In case in the office, we have the electric loads, computers, lighting motors, different activities. They have their own heat loads. They also produce the heat loads. Then in an enclosed space, when you are opening or closing the doors, so from the outside, the hot air comes into the space and so on. So this factors will increase the heat loads on the system. And when we design the system, we have to take these components into account, these heat loads into account. For creating a refrigerating effect, we use in this machine some material, some body, which will absorb heat from the cooling space and that will reject the heat into the environment. So this such a component is known as refrigerant. We will have a wide, very large discussion on this in the next session. So this refrigerant will pick up the heat from the space where you want to create the cooling effect. It will absorb the heat and then it will reject the heat in the environment. Now, while picking up the heat, it picks up the heat in two ways. One is the sensible heat, means while picking up the heat, its temperature rises. So temperature sense is taking place. And second is, it can pick up the heat in the latent way, that is, while evaporating or without increasing the temperature of itself. So by changing the phase, so the refrigerant can pick up the heat in two ways, by sensible heating and by latent heating. So it will get heated up, but the space will get cooled. Now, once you want to maintain any space at a particular temperature continuously, then you will have to supply the refrigerant in the space continuously at a lower temperature than the space you want to maintain at a particular temperature. Suppose if I want to maintain a room at 25 degrees Celsius, then I have to supply continuously a refrigerant into the space in any form at lower temperature than 25, mostly 8 to 10 degrees Celsius lower. So that will be 15 to 17 or 18 degrees Celsius. We will supply the refrigerant into the space and it will come out from the space at 25 degrees Celsius and it will maintain a temperature of 25 degrees Celsius in the space. Let us see that, understand these two with the help of these two figures. Suppose we have this room. In this room, we have a tray of water at 0 degrees Celsius. We have another room. We have the tray of ice at 0 degrees Celsius. The room temperature is 25 degrees Celsius. That we intend to maintain the temperature of room at 25 degrees Celsius. Now what will happen? This water is at 0 degrees Celsius. It will start warming up and room will lose the heat. This water will get the heat. So room will get cooled. In that way, the temperature of the water will increase and this can go maximum up to 25 degrees Celsius. At that point, there will be a thermal equilibrium and no heat transfer will take place here. So that way we can maintain the room at a particular temperature, in this case at 25 degrees Celsius. While doing so, we have inserted insulation all around the room here. So while this cooling is being taking place from outside, though we have inserted the insulation, but still the no insulation is perfect. Therefore, some quantity of heat from outside will penetrate into the room, and this will add up, heating up to this water. And when you maintain a steady state position of heat penetration and heat removal, means whatever quantity of heat is being penetrating into the space, if the same quantity of heat we are removing by some means here with the help of circulation of the water at 0 degrees Celsius, then you will be able to maintain the temperature at 25 degrees Celsius. So this is known as the sensible cooling. This is known as the sensible cooling. Here in the room, second case is latent cooling. Here we have kept some cubes of ice, and that ice is at 0 degrees Celsius at 1 atmospheric pressure. And in this case also, we want to maintain temperature of the room at 25 degrees Celsius. Now what happens? Outside temperature is more than 25. So certainly the heat will penetrate into the space, and this heat will be absorbed by this ice, and ice will get melted. And its temperature of the ice will remain constant till all the ice cubes are melted finally. And in that way, we are also maintaining a temperature of 25 degrees Celsius, in this case, in the room. So what happens? Here, all the heat has been utilized for melting the ice, and the consequence of that is the room is being maintained at a particular temperature. So this type of cooling is known as latent cooling. So that way, we have the two types of cooling here. Now, one more arrangement can be done with the help of ice and with the help of water. Suppose we have the slurry of ice in one compartment, and this is the another compartment you want to maintain at a particular temperature. Here what happens? We are keeping ice at 0 degrees Celsius, or you can say the 4 degrees Celsius, whatever the case may be. You have the ice at particular temperature. Now, through this ice, we are connecting these two compartments with the help of tubes. We have the different tubes, and through the tubes, we are circulating some water or some gas, anything. What happens? When this gas is coming in contact with the ice, it gets cooled down. Then this gas or any liquid will pass into this room here. Its temperature is 1 degree Celsius. So here the temperature is 1 degree Celsius. The room temperature can be maintained to any extent. So the maximum temperature is here 5 degrees Celsius. I want to maintain room at the 5 degrees Celsius. So we are supplying the fluid at 1 degree Celsius. Now it will pick up the heat. Now here the sensible heat is being picked up by this flowing fluid, and its temperature will rise. So at the inlet it is 1 degree Celsius. Now it will go to 3 degree and 5 degree, and it comes back to the, at 5 degree Celsius, it comes back to this ice chamber. So here the ice, now the ice will also get melt because the heat load is coming here. So the portion of ice will get melt, and this will get drained out. So slowly the quantity of ice will carry on decreasing. So we can replace it. If you want to maintain a particular temperature and particular heat load, then you can replace whatever quantity of the ice has got melt and drained out, the same quantity of ice we can replace. So this is how we can produce the cooling effect in a particular space with the help of ice slurries. And this is the oldest base of producing air conditioning or refrigeration in any space. This was the oldest way of doing so. Here also see the ice slab is kept in the room, and from the room air is passing over the ice slab. It is coming in the contact with the ice, getting cooled. Density increases, it falls down. Ice melts, and it is coming out of the drain. So that way what happens? You can maintain the room at a particular temperature. This is the oldest technique of creating the refrigeration system. Now just modify this. What happens? We are replacing ice with the help of some refrigerant in a room. So this is a big room. In this big room, we are keeping in some vessel this R12 gas. This is one of the example. Nowadays, the R12 gas is no more in industry. So this is a old example. We want to create the temperature in this room at 2 degrees Celsius. Now we are keeping liquid refrigerant at minus 29.8 degrees Celsius. At atmospheric pressure its boiling temperature is minus 29.8. So the moment you are keeping this liquid in 1 atmospheric environment at 2 degrees Celsius, now here the temperature is minus 29, here the temperature is 2. From higher temperature to lower temperature region, the heat will automatically flow. And what happens, it will pick up the latent heat and the part of the R12 will get evaporated. Once it gets evaporated, it will generate the cooling effect in the room, because from the room itself, it is picking up the heat. Now the portion of R12 will evaporate at 1 atmospheric pressure. And from here, this is going out. This is the vent. So whatever quantity of refrigerant is evaporating, it is going out in the atmosphere. This is one of the example. Simple. So that way, by evaporating the liquid, you can generate the cooling effect in any given space. That way we can produce the refrigerating effect. Now, where it is taking place, its name is given as evaporator, because the liquid is evaporating. Now, we can modify this simple crude method further. What happens? Now, I want to maintain whatever was here, this was a free vent. So whatever the vapor was evaporating, it was going out. Now I put up some control here and I can regulate the amount of vapor coming out from here. So that can be done here. We are putting some throttling device. What happens? Initially, whatever the refrigerant was getting evaporated. Now, we are not allowing all the evaporant or the vapor to come out. So part of the vapor is coming out and part is remaining in this chamber. Now here the pressure will increase. So previously in the previous case it was 1 atmospheric. Now here it is 3 atmospheric. In previous case at 1 atmospheric pressure, the boiling point was minus 29.8 degrees Celsius. Here the pressure has increased. Now the boiling point has also increased, that is minus 1 degree Celsius. So here the refrigerant is getting evaporated at minus 1 degree Celsius. Room is being maintained at 2 degrees Celsius. Now what happens? Here all the refrigerant was going in the atmosphere. So it was just wastage. Now I want to solve this. अब हम क्या करते हैं कि यहाँ पर we install some component, that is a compressor. So whatever refrigerant was going out, we are just picking it up and sending to the next component, that is the compressor. This compressor is pumping it out. So here it was going in the self way into the atmosphere. Now it is going through a compressor. So we have picked up vapor from here. We have supplied to the compressor. Now here also see some other refrigerant has been refrigerant 12 same. Now we are maintaining temperature as minus 66 degrees Celsius. Here the temperature is, the pressure we have reduced, because here the compressor is picking up the vapor. So it will pick up faster. Therefore, here the pressure will reduce in this chamber. In the evaporator, the pressure will reduce, and this pressure is 0.1 atmospheric pressure. And corresponding to this, its temperature is minus 73.2 degrees Celsius. Minus 73.2 degrees Celsius. And the space temperature is minus 60 degrees Celsius. So that way I can create a very low temperature in this space by just incorporating this compressor. What happens? One more control device has been incorporated here. A high pressure fluid we are supplying, and we are keeping here some needle valve at the outlet of this high pressure supply zone, and we maintain a particular low pressure liquid in this chamber with the help of some float valve, and this evaporates at some particular temperature, and that way also we can generate some particular temperature in this space, as this vapor is being picked up by the compressor and supplied to the next component. Now here one more component is there. This was a needle valve. Here some other sensor has been incorporated. This sensor controls the quantity of refrigerant going into the space through this pipe, that is the evaporator. With the help of some sensor, we will discuss later on. This is a thermostatic expansion valve. A low temperature is maintained here, and depending upon what it senses, that much quantity of refrigerant is supplied from this receiver or supplying agent. And that way, here also we can create some temperature in the space. Now, so long as we have seen from the compressor, we were rejecting the atmosphere, the refrigerant into the atmosphere. Now we are going to salvage the complete refrigerant. We are not going to waste the refrigerant anymore. So different components have come into the cycle. So this is the space chamber. In the space chamber is the evaporator, where the low temperature, low pressure refrigerant is evaporating. We are picking up with this low temperature, low pressure refrigerant through this pipeline by this compressor. And this compressor will compress it to a high pressure, high temperature, and this will reject to the next component, that is the known as the condenser. Behind the condenser, we can keep this condenser open to the atmosphere, or we can circulate certain quantity or adequate quantity of atmospheric air on this surface. This will get condensed, and this will come out as a liquid, and this will be stored in this vessel. This vessel is known as the receiver. And from this receiver, we can control the amount of refrigerant going to the evaporator. So what happens? This cycle, now this has come out to be a complete cycle. Now this becomes a closed cycle. My refrigerant is circulating all along the pipelines through the different components, and refrigerant is not let to be out to the atmosphere. Once we have filled up the refrigerant in the compressor, in the system, the same refrigerant will carry on till life unless there is leakage due to any reason in the system. The same has been shown in this. This is a typical refrigeration cycle, vapor compression refrigeration cycle. Here we have the compressor. This compressor receives vapor from the evaporator. यहाँ पर जो था वही from the evaporator. It is being compressed, high pressure, high temperature vapor. Now it comes to the from condenser. At the outlet of the condenser, we have the liquid. At the inlet of the condenser, we have the pure vapor or the gas, and in the condenser, we are rejecting the heat to the atmosphere, and liquid is coming from here. Now this liquid is let pass into expansion device. This expansion device will reduce the pressure, and ultimately the temperature will get reduced, and this low temperature, low pressure liquid is supplied to the some next component, that is the evaporator, and this evaporator can be used for different purposes. Now for air conditioning, suppose you want to use, we can supply air over this pipe, over this condenser. We can cool the air, and that cold air can be supplied to any chamber, so that will become a air conditioner. This pipeline or this evaporator can be put into what? Into a water. That water will get cooled, and that will be known as the water cooler. This can be used into milk, so this will become the milk chiller. So depending upon our requirement, we can utilize this for the different purposes. So this is how a simple vapor compression cycle is functioning. Now it has the two regions. One is the high pressure side and one is the low pressure side. So high pressure side is the compressor, condenser, and this expansion valve, 50%. Now part of the expansion valve, evaporator, and part of the compressor, this comes into the low pressure side. As we know, we are using some liquid refrigerant, some refrigerant in the system. So it will have some property and there is some phase change of this. So this is shown as the how the phase change of the refrigerant take place at a particular pressure or at a particular. The state one is the refrigerant is at 1 atmospheric pressure and 20 degrees Celsius. When you supply heat, now this becomes, in case it is saturated, so you just take one example here. Suppose this is unsaturated, then this is subcooled. Suppose it is subcooled, when you are giving the heat, this will expand and this will come to the saturated liquid state. Further heating will give latent heat of evaporation. This will evaporate up to this point. So from here to here is the phase change. And from here, if you are giving the further heat to the system, it will get superheated. So this is the graph. And this graph is at the different pressure. Same is the temperature and volume graph. Here also at 1.1 megapascal, this is the solid state or not solid state. This is the subcooled region. If you are heating at state 1, that substance refrigerant will get heated up and it will go to the B point. B point is the saturated liquid point. This was the subcooled region. So A to B is the sensible heating. At the B point, since it is coming at a saturation level, so now further heating will cause the phase change. So from B to C, it will evaporate and it will pick up the heat from the surrounding in the evaporator. And at C point, it is completely evaporated. Suppose unit mass of the refrigerant was available in the saturated state at B, then the same refrigerant will be at C point in evaporated state. So from B to C, it has picked up the latent heat of evaporation and it has changed its fate from liquid to vapor. Now here at C point, it becomes the complete gas. There is no liquid particle. And from C to D, if you are further heating this refrigerant, then this will become superheated vapor. So this curve is at the different pressure levels. Now the maximum temperature here is the critical temperature. As you compress it, its temperature will rise, its pressure will rise. It is at the critical point. In the case of water, the critical point is 373 degrees Celsius and 22.09 megapascal is the critical point. Now this is the pressure volume diagram. Same thing happens in the same data has been interpolated, same process has been interpolated or at the pressure volume coordinates. So at a particular temperature and pressure, suppose this case we are heating up, its volume will increase, and this is the saturated vapor volume, this is the saturated liquid volume, and so on. At this point, this is the critical point pressure and critical point volume. This critical point से लेकर के जो लेफ्ट साइड का जो कर्व है, the curve at the left side is known as saturated liquid line, and the curve at the right side, this is this way, this is known as saturated vapor line. Escape is not required. Now, these are some triple point data of different liquids. So the water के case में जो है, that is 0.01 degree Celsius temperature is the triple point temperature, and 0.6113 is the triple point pressure of. At the triple point, any substance will coexist in the three states, that is solid, liquid, and gas. So this is the case of, this is the example of the water and other materials that I have been tabulated in this. Now see, in the refrigeration, actually what happens when we are doing the calculations and all, this property table is required. Now, this is the PV diagram of some refrigerant. This curve is the saturation curve, saturated liquid line, and this curve is the saturated vapor line. In between these two curves, the region is liquid and vapor region. Left side of the saturated liquid curve is known as the subcooled region, and right side of this vapor curve is superheated region. So the property changes from this point to this point, the property changes, and this property have been tabulated by the different experiment at the different temperature and pressure, and they are given in the tables, and the same table data is plotted on the graph also. So this is one of the typical example of some refrigerant at a saturation level. So saturated liquid and saturated vapor. Two data you can get the different properties. See here, the temperature is 90 degrees Celsius saturation temperature. Now saturation pressure will be 70.183 degrees Celsius. Liquid saturated volume will be 0.001036, and the saturated vapor volume will be 2.3593. So you can see from the liquid to vapor change, there is a tremendous change in the volume. So this happens actually in the evaporator, where we are creating the refrigerating effect. So this data can be mathematically we can find out here. So VFG, that is the change in volume during evaporation, that is the VG minus VF. So this property is, VG is the volume of the saturated gas, and VF is the volume of the saturated liquid. So this much volume change takes place during evaporation of the refrigerant. This is a very important curve in refrigeration field. Pressure enthalpy diagram. This is for a particular refrigerant. Here the left side curve is, you all might be knowing, this is the liquid line, this is the saturated vapor line. In between, this is the liquid plus vapor line. Here, this is a specific constant volume lines. This line is the constant entropy line, and this is the isothermal lines. This is the constant temperature lines. So you can say the temperature line is almost vertical in the liquid region. It is horizontal in the mixture region, and it is inclined coming downwards in the superheated region. So this way, this is a pH diagram, and जो हमारा students हैं, they must be very familiar with this pH diagram, because this is most widely used for all the calculations in the field of refrigeration. This is also one of the pH diagram for a particular refrigerant, that is R245FA. This is temperature entropy diagram. This is also one of the most widely used diagram for calculation purpose. This is once again saturated liquid line. From here, critical point to right side, this is the saturated vapor lines. Now, in between, this line is a constant pressure lines. This is a constant pressure lines. This red line is a constant enthalpy, yeah, specific enthalpy is kilojoule per kg. So this all must be, a student must know how to find out or how to plot this graph. The same data is tabulated in the tabular form. Now with this basic knowledge how to plot the graph and what is the basic cycle of the refrigeration, we come into the second part, that is the system analysis part. यहाँ पर हम देखेंगे कि परफॉर्मेंस मेजरमेंट, हाउ टू फाइंड आउट पर्टिकुलर परफॉर्मेंस, हाउ टू measure the performance of ideal cycle, real cycle, and refrigerator and heat pumps. In refrigeration field, one term is coined, that is the refrigerating effect. This is the most widely used, and students must be very much confident of this, what actually the refrigerating effect is. So whatever cooling effect we are generating in the evaporator or in the cooling space, so that space is, that cooling effect is known as refrigerating effect. And this you can find out, it is defined as the quantity of heat extracted from a body or a space to be cooled in a given time. So we show this by N, heat extracted from the cold space in a particular time region. Now, a refrigerating effect, based upon this refrigerating effect, we grade the, we give a rating to the refrigerating machine, that is ton of the refrigeration. So refrigeration capacity कि कौन सा मशीन या कौन सा एसी कितने कैपेसिटी का है, which machine is of what capacity, that we give a rating capacity, and we know this is known as ton of refrigeration. So in the field of ton of refrigeration, we have two types of tons. One is the metric ton and one is the short ton. So metric ton is 1000 kg and short ton is 2000 pound, that is 907 kg in SI units. And in refrigeration system, this ton of refrigeration is calculated based on short ton, not on big ton. So what actually the ton of refrigeration is? So we are melting ice at 0 degree Celsius, 1 ton of ice, 1 ton of soft ice, that is 2000 pound of ice, yeah, 907 kg of ice we are melting at 0 degree Celsius in 24 hours. And whatever cooling effect is generated, that cooling effect has been given a name, that is 1 ton of refrigeration. And if the same quantity of cooling effect is generated by our any refrigerating machine or AC or refrigerator, then we say that our machine is of 1 ton capacity. And in that multiple, 2 ton, 3 ton, 4 ton, 5 ton, and so on. So how much it is coming in kilowatt can be calculated. So see, the ice must be at 0 degree Celsius, because at 0 degree Celsius, at 1 atmospheric pressure, when you supply the heat to the ice, it will just get melt. So 1 ton of refrigeration can be calculated as 334 multiplied by 1000 kg. So 334 is the latent heat of fusion for the ice. 1 ton of ice is 1000 kg, that is the big ton, in 24 hours divided by 24 hours. And you calculate it by 336, 24 into 60 into 60, it comes out to be kilojoule per second. So this comes out to be 3.86 kilowatt or 3.5 kilowatt. So 3.86 kilowatt is based upon the big ton, and when you are using the short ton, or a small ton. So this will come out to be 3.5 kilowatt. One more term we are using in performance analysis, that is coefficient of performance. Coefficient of performance is said to be whatever cooling effect or whatever desired effect we are obtaining at what cost. So this is the cooling effect we are generating divided by the energy we are spending, that is the work input. So QL upon W in. So this is a refrigerator, same figure. This is the cold space. In the case of refrigerator, this is the freezer. So in the freezer, we are producing the cooling effect. Here in the compressor, we are supplying the heat energy, the work energy, that is the electrical energy. And that way, we are producing the cooling effect. So how much quantity of cooling effect has been generated here, divided by how much quantity of energy input has been given to this, and this 2 ratio is known as COP. COPR stands for the refrigerator and COP-HP stands for the heat pump. In the same case for the heat pump, here we are supplying the some quantity of heat to the room you want to heat it up. So supply heat will be here QL plus W in. So W in is the work input, QL is we are abstracting the heat from the cold space, and these two are combining here, and this goes to the atmosphere, or if you supply to a house, the house will get heated. So this is known as, so this will function as a heat. So COP of refrigerator is QL upon Q in, and this is for heat pump QH upon W in. There is a relation between COP refrigerator and COP heat. So this relation is COP heat pump is always 1 greater than the COP of refrigerator. This is always more than the refrigerator, and by quantity 1. Basic cycle. This is the reverse cycle upon which the refrigerator works. Reverse Carnot cycle. You all must have studied. We have the 4 components: compressor, condenser, turbines, and evaporator. Compressor will receive the cold fluid at point 2. So this is the TS diagram. So at point 2, it is coming to the compressor. 2 to 1, 2 to 3 we are compressing in the compressor. 3 to 4 is the condensation. Here we are rejecting the heat to the atmosphere at the high temperature. At 4 point, this is coming out from the condenser as a liquid, saturated liquid. So from condenser, 4 point is coming. Now this liquid at high temperature, high pressure is supplied to the turbine. And in the turbine, the expansion is taking place, reversible adiabatic. So this is the vertical line. 4 to 1 is the expansion in the turbine. At point 1, the temperature is very low. This low temperature refrigerant or liquid we are supplying to the evaporator. From where you want to remove the heat. So this will remove the heat. So QL quantity of heat is being removed from 1 to 2. So from 1 to 2, the phase change. Now here the heat is being absorbed, and here the heat is being rejected. Now the COP of reverse Carnot refrigerator is 1 upon TH upon TL minus 1, where TH is the highest temperature of the cycle and TL is the lowest temperature of the cycle. So that is, at what temperature the heat is rejected and what temperature the heat is being absorbed. So here the temperature of the space you want to maintain is the TL, and the temperature of the space where you are rejecting the heat, that is the TH. So this is COP of air, and COP of heat pump is 1 upon 1 minus TL upon TH. Now with this knowledge, we come on the practical ideal we are using in domestic refrigerator or in our window AC or any refrigeration plant. So here this is the component figures. This is the TS diagram of simple vapor compression refrigeration cycle. Once again, the same thing, the compressor will receive the refrigerant from the evaporator, dry saturated vapor. It will compress and deliver high temperature, high pressure gas, and it will supply to the condenser. Just see here on the graph. This is the saturated liquid. This is getting evaporated in the evaporator. It is coming out at 0.1 saturated vapor. It is going to the compressor. Coming out from the compressor at 0.2. It is in superheated region. Now from 2 up to this point, it is getting desuperheated, and from here, so we are desuperheating it till it becomes saturated vapor, and from this point, further cooling will produce the condensation of the gas. So it will change the phase. It will come out to be liquid refrigerant here. Heat will be rejected at high temperature. Now at 0.3, we are passing this refrigerant through a device that is the expansion valve, and here the expansion is irreversible expansion, and it is not isentropic, it is irreversible expansion. 3 to 4 is irreversible expansion, and here at 0.4 it will go to the refrigerant will go to the evaporator. It will pick up the heat from the evaporator. It will cool down the substances kept in the evaporator, and it will get evaporated, change its phase from liquid to vapor, and it comes here, and the cycle continues. The cycle repeats so long as the electricity is given to the compressor. So this is the simple vapor compression cycle, because here the vapor coming out from the evaporator is the saturated, and here the liquid coming out from the evaporator is saturated. So since these 2 points are saturated points, therefore we call this simple vapor compression refrigeration cycle. Now here, for the same COP of vapor compression cycle, in this case, simple vapor compression cycle, so refrigerating effect is taking place in the evaporator. From 4 to 1, heat is being absorbed. So QL quantity is being absorbed. So this is the QL. This is our desired output, and we are spending work input 1 to 2. So 1 to 2 is net work we are supplying. So this 2 ratio is the COP of refrigerator, and in the form of enthalpies, we can say H1 minus H4 is the refrigerating effect or cooling effect we are producing, and H2 minus H1 is the energy input we are giving to the device. So ratio of these two is known as COPR. For the COP heat pump, this is the QH upon W in. So QH what we are supplying to the hot body. So that is H2 minus H1. Sorry, H2 minus H3. जो कंडेंसर में आपका हीट जो रिजेक्ट होता है, that heat is being supplied to the hot spirit. So H2 minus H3 we are in the case of heat pump divided by H2 minus H1. This is the working. So this is the ideal vapor compression cycle COP relations. Ideal vapor compression refrigeration cycle, just see, same thing. Here, heat is being absorbed from 4 to 1, heat is being absorbed. 1 to 2, work is being supplied. That is, we are supplying the electricity in the case of a refrigerator to the compressor, and 2 to 3, heat is being rejected. So ये दो इसका ग्राफ है, TS and PH. So on these two graphs, the different processes have been shown by these arrow lines. So here Q in minus Q out is so here अब आपका यहाँ का H1 आप कैसे देखेंगे? How you can find out H1? So H1 you can see from the graph. तो जो भी रेफ्रिजरेंट हम यूज करेंगे इस साइकिल के अंदर में उसका ग्राफ निकालेंगे पीएच डायग्राम, और उसका हम पीएच डायग्राम से डायरेक्टली इसका डाटा ले सकते हैं या टेबल से प्रॉपर्टी टेबल के डिफरेंट टेबल से हम इसका इस पॉइंट 1 का वी कैन फाइंड आउट द एंथैल्पी एट पॉइंट 1, एट पॉइंट 3 एंड पॉइंट 2 एंड पॉइंट 4. The same cycle is being represented on pH diagram, actually on the pH diagram. So see, this is saturated liquid line, this is saturated vapor line. So outlet condition from the evaporator is at vapor line, so point 1. Now compression is taking place along this line, that is constant entropy line को हम follow करेंगे till a pressure line cuts this. कांस्टेंट प्रेशर लाइन यहाँ से आपका ये जो है दिस इज टीएस डायग्राम एक्चुअली. तो यहाँ से देखेंगे कि सैचुरेशन टेम्परेचर क्या है, उस टेम्परेचर लाइन को यहाँ से जो प्रेशर लाइन जा रहा है वो कैसे कट करता है, इस पॉइंट पे हम ये आइडेंटिफाई कर लेते हैं. फिर यहाँ से हॉरिजॉन्टल लाइन ड्रॉ करेंगे, ये सैचुरेशन को कहाँ कट कर रहा है, इस पॉइंट पे. अब इसके पीछे निकल रहा है, 3 पे निकल रहा है, सो दिस इज सब कूलिंग. नाउ फ्रॉम 3 to 4 जो भी आपका इवापोरेटर प्रेशर है उस प्रेशर लाइन को आप यहाँ से कट कीजिए वर्टिकल लाइन ड्रॉप करके. सो दिस बिकम्स द इनलेट कंडीशन टू द इवापोरेटर. दिस इज द आउटलेट कंडीशन फ्रॉम द कंडेंसर. दिस इज आउटलेट कंडीशन फ्रॉम द कंप्रेसर and this is inlet condition to the compressor. So 1, 2 is the compression process, 2, 3 is the condensation process, 3, 4 is the expansion process, and 4, 1 is the evaporator process is taking place. So work input will be S2 minus H1 is the work input. Heat rejected is S2 minus S3, and heat absorbed will be H1 minus H4. So you can find out the COP, actual COP from this graph, H1 minus H4 divided by S2 minus H1. This will give you the COP of this cycle. सेम रेफरेंस साइकिल एक पीपी डायग्राम के ऊपर इसको ड्रॉ किया है. सेम वहां पर ये आपका इवापोरेशन है अप टू द सैचुरेशन पॉइंट. This is compression process, then this is condensation process, and this is expansion process in the throttling device. So this region is the liquid plus vapor, this is the vapor, and this is the liquid, subcooled liquid. आप एक सिंपल एक हाउस होल्ड रेफ्रिजरेटर को आप देखिए, सबके घर में होगा. यहाँ पर ये हमारा फ्रीजर है जहाँ की इवापोरेटर आता है. ये आपका डिफरेंट जोन्स है, अलग अलग टेम्परेचर जोन्स है. सबसे लोएस्ट है नीचे आपका क्रिस्पर, और ये जोन जो है ना आपका डिफरेंट जोन है जो कि अलग अलग टेम्परेचर रीजन होगा इसका. वी कैन पुट द डिफरेंट आइटम एट द डिफरेंट टेम्परेचर्स इन द रेफ्रिजरेटर. सो लोएस्ट टेम्परेचर इज हियर एट द फ्रीजर and the highest temperature is here at the crisper where we are putting the vegetables and rolls. ये हाउस होल्ड रेफ्रिजरेटर का देखिए, दिस इज फ्रीजर, दिस इज कंडेंसर, एंड दिस इज कैपिलरी ट्यूब, एंड दिस इज कंप्रेसर. तो यहाँ पर अलग अलग रीजन आपको फ्रीजर रीजन में दिया हुआ है. -18 डिग्री का टेम्परेचर भी आर मेंटेनिंग. बॉडी के अंदर में हम +3 डिग्री का टेम्परेचर मेंटेन करते हैं, या नीचे क्रिस्पर के आसपास आपका 3 डिग्री का टेम्परेचर मेंटेन हो रहा है. अलग अलग पोजिशन में अलग अलग टेम्परेचर आपका मेंटेन है. यहाँ देखिए, सो -18 डिग्री सेल्सियस इज द फ्रीजर टेम्परेचर, 0 डिग्री इज द मीट जोन का टेम्परेचर उसके जस्ट नीचे होगा, Then cooling zone that is from here, from this point to this point, from this point to this point is the cooling zone. So here the temperature is 5 degrees Celsius, and the crisper, the bottommost portion, the bottommost here, the temperature is somewhere 10 degrees Celsius. Now, अभी तक जो हमने देखा है, this all was theoretical. When we come to the practical cycle, so practical cycle is the actual vapor compression cycle is bit different. थोड़ा सा इसमें difference है. Difference क्या होता है? What actually the difference is? Nothing is ideal in this world. So the compressor will not be as ideal compressor. This condenser will not be ideal. This evaporator will not be ideal. This expansion device will not be ideal. They all will have some irreversibilities. So due to irreversibilities, some heat is generated, some energy is lost, excess energy is consumed. And depending upon that, when we draw the cycle is this way. So here in the evaporator, we have seen that at constant pressure evaporation, but in actual cycle, it is from 7 to 1, 7 to 8. 7 to 8 is the evaporation. During evaporation also, the pressure is reducing because there is a friction in the pipelines, the friction in the evaporator pipelines. So due to this pressure will drop. Then there will be further drop of the pressure when the valve opens at here. Now from 8 to 1, there is some superheating. We are doing some superheating or some heat is coming out here. तो यहाँ पर भी आपको constant temperature पर नहीं हो रहा है. Now it is getting superheated. From 1 to 2, this is the ideal. But 1 to 2 on this is ideal, means isentropic, but this is not taking place. What takes place is 1 to 2 dash. This one. Here from this point to 4, this would have been the ideal horizontal line, but it is not taking place because there is a pressure drop. Once again, there is a friction in the pipelines, so pressure will drop. So from this point to 5 point, the pressure is dropping. Therefore, this line is now inclined. Now here 4 to 5, here once again there is a further pressure drop. Then 5 to 6 is taking place in the expansion device. So this is the deviation from the ideal cycle. The same thing has been shown in this figure also. Practical refrigeration cycle, you can see just here. Practical refrigeration cycle. आपका 7 to 2, 7 to 1 is the evaporating. Now 1 to 2 is superheating because from the evaporator, the vapor is coming out, going to the compressor through the pipelines. So on the way, it will pick up the heat from the environment. So it will get superheated. So this 1 to 2 is not taking place in the refrigerated space. So this is the extra load on the compressor. From 2 to 3 here, we are compressing. So due to this extra load, 3 point will shift to the right side and this will consume extra power due to this. Then 3 to 4 is the desuperheating. 4 to 5 days is cooling. That is the condensation, heat rejection at constant pressure, constant temperatures. So heat rejection in the condenser is taking place from 4 to 5. 5 to 6 is taking place. Some in the outer part of, in the last part of the condenser, we are doing the extra cooling of the substance, that is subcooling, and that is the outlet condition of refrigerant from the condenser is the 0.6. From 6 to 7, this is taking place in the expansion device. That is in the case of refrigerator, it is capillary tube. It is capillary tube. Now 7 to 1 is once again this evaporation. So this is different processes are being shown in this graph. So this is compression process, this is desuperheating, this is heat rejection or condensation, this is subcooling, and this is expansion, and this is evaporation. See the practical here in the actual cycle. But what happens in the actual cycle? 6 to 7, this would have been horizontal line. But there is a pipeline friction, so pressure will drop. So this 7 will not be here, it will be bit lower. So there is a pressure drop. Now here at point 7, it goes to the compressor, inlet to the compressor. So while going to the compressor valve opens at this point. So once the compressor valve opens, there will be pressure drop. So 7 to 1 is the pressure drop in the suction section. Now from 1 to 1 dash, 1 to 2 should have in the compression. But when you open the outlet valve, so the pressure will drop. So therefore, to take up that pressure drop, we do the excess compression in the compressor up to 0.1, so that when it is coming out, it comes out at the condenser pressure. So condenser pressure is 3. Now यहाँ से 2 to 3 is desuperheating. Now 3 to 4 should have been the ideal condensation, but the dotted line is giving the actual line. So here the pressure drop is taking place. See the 5 point is here. Now here from 5 to here, what happens is this is expansion. Now advantage of this pressure drop is what happens? There is a 4 and 5 में shift है थोड़ा सा left की ओर आ रहा है. So there is some advantage here because refrigerant is available at more supercooled region, and here the 6 point is shifting to the left side. So more refrigerating effect can be generated in the actual cycle due to this pressure losses. But this gain in refrigerating effect is badly adversely affected by this loss in pressure loss here or extra energy required in the compression process. So this gain is nullified. So this is the pH diagram, and this is the pH diagram for this actual cycle. Same we have done. We have established here on this pH diagram the different components. Here the compressor. Now 1 to 2 is the ideal compression. 1 to 2 dash is the actual compression. Now 2 to 2s is the desuperheating. Now here we have installed the condenser. Now 3s to 3 is this is the subcooling, and at point 3 we have installed some sort of expansion device. So expansion valve. 3 to 4 is the expansion process. So the outlet from the expansion device is mixture of saturated liquid at 4s and saturated vapor at 1s, and the state is 4. So from 4 to 1s is the evaporator, and here the suction of the heat or refrigerating effect is taking place.
Sir, do you want to take a break? 10 minutes break?
Any doubt? Yes, we can.
Okay, so I will now request the participants to place their queries on the YouTube comment box so that we can place it to the expert. And you can take your time. We'll take a 10 minutes break. In that time, you can put up your comments, and then we will be asking expert about those queries. For 10 minutes,
Okay.
sir, you can take a break. And please don't log out of YouTube. And Jimmy, please stay online. Just close your camera and your mic. We'll meet at 12.
Okay.
Sir, you can close your camera and your mic, or whatever is convenient. Whatever is convenient, because we are live on YouTube. सर स्टार्ट करें, shall we start? Pathak sir, I cannot see you or hear you.
Yes, we can now start.
Alright sir, so your screen is not being presented. Before I start, I will request the participants to write their questions on the YouTube chat box so that it can be placed to the expert. While expert is putting up the presentation, I would request all of you to please keep writing on the chat box because your questions will make this training little more bit more interactive and interesting. So I am looking at the chat boxes for your queries. Meanwhile, I will request sir to please continue.
My screen is shared now.
Yes, sir.
Thank you, madam. From the previous topic, now the refrigeration cycle, one refrigerator can be also used as a heat pump. Means, there is a question asked, can we use our air conditioner as a heater in the winter and cooler as a summer? The answer is yes. We have to install one reversing valve on our AC, and with that reversing valve, you can use the same air conditioner as a heater in the winter and as a cooler in the summer. So this is the design of a reversing valve. This is the four-way valve है यहाँ पर. Just see here. This is the compressor. From the compressor, the hot gas is coming to this valve. Now suppose we want to make it as a refrigerator. Then what we do? We supply from this valve through this outlet. This goes to the condenser, and this is the condenser. So this will be outside, and then it will go to the expansion device, and this is the evaporator, the room side, and this will generate a cooling effect. This will generate a cooling effect. So this will act as a AC. Now the same AC I want to make it as a heat pump or the heater in the winter. So what we can do, here the same reversing valve position can be changed. Now the gas from the compressor is coming to this reversing valve. Now it has some remote control. You can put it into as a heat pump or as a refrigerator mode. So now if you put in the heating mode, then this hot gas will be directed to the room side. That is where the previously this was a evaporator. Now this will act as a condenser. This will act as a condenser. Now since it is fitted in the room side, so this hot gas is coming in this evaporator. Now it is acting as a condenser. Now here it is getting condensed, then it goes to the expansion device, then it goes to the condenser. Now this condenser is the previous condenser. Now this will act as a evaporator. So the hot gas is now diverted back to the room side. So room will be heated up. Now this goes to the condenser side. Now it is acting as a evaporator. So outside will be cooled. So instead of reversing the AC, window AC, you can just install this valve on the AC, and with a remote control you can act it as a AC in the summer season, and heater is a heater in a winter season. So one extra device, this is installed on the any window AC or on any split AC. So this we will escape. Now we are having the Breton cycle, that is the gas refrigeration system, which we are using in the aircraft. So in aircraft we are using gas air refrigeration system. This works on the principle of Breton cycle. We have one compressor, one combustion chamber, one turbine. This is the Breton cycle. When you reverse the Breton cycle is used for the turbine, jet engine. So here the compressor is 1 to 2 is 1 to 2 is the compression process. 2 to 3 is heating process in the combustion chamber. Now this hot gas is expanded in the turbine or in the jet. So jet propulsion take place, and 4 to 1 is the heat rejection somewhere in the atmosphere. अब इसी को यदि हम रिवर्स कर देते हैं, जब हम इसको रिवर्स करते हैं तो दिस विल एक्ट एज ए रेफ्रिजरेशन साइकिल. अब इसमें क्या देखिए, दिस इज द फ्लो डायग्राम, दिस इज द कंप्रेसर, दिस इज द हीट एक्सचेंजर, दिस इज द टरबाइन एंड दिस इज द हीट एक्सचेंजर. तो कंप्रेसर में क्या होता है कि जो एयर हम यूज करते हैं, एयर टरबाइन कंप्रेसर में फ्यूल को बर्न करने के लिए जो हम एयर कंप्रेस किया जाता है, द सेम एयर कैन बी यूटिलाइज्ड फॉर प्रोड्यूसिंग द एयर कंडीशनिंग इन द एयरक्राफ्ट. The reason is we are using air conditioning in aircraft because we can't install a separate machine on the aircraft because that will increase the payload of it. Therefore, what happens? Part of the air from the air compressor is taken. Now this is cooled in a cooler. Some cooler will be there. We cool it in the cooler. Then we send it to the turbine. In the turbine, we are expanding. So some work output will be obtained here. Now, when the normal air is expanding in the turbine, it gets cooled. Means its outlet temperature will be less than the environment temperature. Now that low temperature air can be supplied in the cabin, in the cockpit, and a particular temperature can be maintained in the complete air. So this is the flow. This is a component diagram. Now let us come on the TS diagram. TS diagram में देखिए 1 to 2 is isentropic compression. We are taking the ram air, that is from the atmosphere. We are taking the air. We are compressing in the compressor of the aircraft. Then we are cooling 2 to 3 in somewhere in the component, that is the cooler. And 3 to 4 we are doing expansion in the turbine. And at point 4, the temperature is less than the inlet temperature of the air. So this cool air can be now supplied to the cabin and the room, and heat will be picked up from 1 to 2. So this is how we are doing aircraft gas refrigeration system. The same thing has been shown on the PV diagram. 1 to 2 is the compression, 2 to 3 is the heat rejection at constant pressure, 3 to 4 is the expansion in the turbine, and 4 to 1 is the constant pressure heat absorption process in the cabin or in the cockpit or in the different components. In gas refrigeration, we can just increase the efficiency of the gas refrigeration by incorporating some components within the cycle. So see, just this is known as the gas refrigeration cycle, some modification, how the efficiency can be increased. Here compressor का आप ये देखिए 1 point में आपका this is the inlet point to the compressor. So one is the inlet point to the compressor here on the TS diagram. On the flow diagram पर यहाँ देखिए 1 point में है आपका compressor में inlet, 2 point में यहाँ से निकल रहा है, 2 point में यहाँ से निकल, अब यहाँ से compressor से निकला, it goes to the next component, that is the heat exchanger. So at point 3 on the TS diagram, dot is given, it goes to the heat exchanger. We are rejecting some heat to the heat exchanger. Now this is cooled. Now this cooled air is now supplied to the turbine at point 4. And we are getting low temperature gas at 0.5, and this low temperature gas is supplied to the place you want to cool down. That is the cabin and the cockpit. So 5 to 6 is here. The 5 to 6 is heat absorption process. See here, heat is being absorbed, cooling is being maintained here. Now 6 to 1, it goes back to the compressor, and so on. This cycle continues. Now, how to make the improvement? How to make the improvement in the cycle? See, in the heat, after the heat exchanger, one more regenerator has been installed in the cycle. So what happens? From the compressor, the hot gas is coming to the heat exchanger. It is partly cooled here to the maximum what can be with the help of atmospheric air. Now further it is sent to the regenerator. See, in the regenerator, this gas is coming in this portion, and from heat exchanger, that is from the cabin and cockpit, the air is being either that has to be rejected to the atmosphere, but still it is cooled. So this cold air can be utilized for further cooling the hot air which has come out from the heat exchanger. So what happens? This 3 to 4 is taking place, 2 to 3 was taking place, cooling was taking place in the heat exchanger. Now 3 to 4 is further cooling is taking place in the regenerator. So what happens now? The entry point to the turbine is improved. That is, at low temperature we are supplying gas to the turbine and expanding in the turbine. What will happen? The net effect will be the outlet temperature of the turbine will be very, very low, and this low temperature can be sent to the cabin or the cockpit. So this is the improvement. So if we had not incorporated the regenerator, we would have supplied air to the turbine at point 3. But by incorporating the regenerator, now we are supplying the air to the turbine at point 4. So 0.4 temperature is less than the 0.3 temperature. Therefore, the outlet temperature from the turbine 0.5 is more less than what would have been obtained if we had supplied air to the turbine at 0.3. So this way we can improve the COP or efficiency of the air refrigeration system in the aircraft. Now we will move to the refrigerant parts. In the discussion, we will be mostly discussing about how to select a refrigerant, then how the refrigerants are qualified, then difference between the primary and the secondary refrigerants, refrigerant selection criteria based on the thermodynamic, thermophysical, environmental, and economic properties, and how the refrigerants are designated, how the designation or coding is given to the refrigerants. That will be discussed in this part briefly. Okay. Now, refrigerant is the primary working fluid we have already discussed. This will absorb the heat at one point in the cycle and reject the heat at some other point in the cycle. That way, it will create the cooling effect at the point where it is absorbing the heat and the heating effect at the point where it is rejecting the heat. Refrigerant can be in any form, the solid, liquid, or gaseous forms. The solid, for example, is already given in the beginning, that is the ice. Liquid form refrigerants can be, mostly we are using the refrigerants in the liquid form, and in the gaseous form, the air is used as a refrigerant in the gaseous form. Now, in vapor compression cycle, we absorb the heat, or the refrigerant absorbs the heat while it changes the phase in the evaporator. So when it evaporates in the evaporator, it will change its phase, it will pick up the heat, and when it rejects the heat in the condenser, it will reject the heat and it will condense. In air cycle, there is no phase change, only sensible heating or sensible cooling takes place. So we will be focusing on mostly on the liquid refrigerants we are using in the practical cycles or in the practical equipments. The thermodynamic, we all want that the refrigerating component must be very efficient. So efficiency of thermodynamic efficiency of any components depends upon the temperature range upon which it is operating. Then it is not only the temperature range, this is the ideal case, but due to the environment regulations, we have some restrictions. So environment issues are like ozone depletions, global warmings. So due to this, all the refrigerants nowadays, which are more thermodynamically efficient, cannot be used on the machines because of these restrictions. Previously, we have been using R12, R11, R22. These were the refrigerants mostly used between 1930 to 65 and 70, even up to 90s. But later it was found that they are causing the ozone depletion, which was detected in 1974. And many regulations have come up to phase out these refrigerants to protect the environment. So some replacements have come out. And these replacements are for chlorofluorocarbons, because the chlorine component is the major culprit which is causing the ODP. So those replacement part will be discussed. Now let us come to the refrigerant. We have the primary refrigerant and the secondary refrigerants. Primary refrigerant is basically used in the cycle directly where it is absorbing the heat where you want to create the refrigerating effect. Suppose the example is R12, R22, R134A. So in a cycle, we are using this and we are creating a direct refrigerating effect or the cooling effect in the space or in the component we need. But there are some refrigerants which are used, which are cooled by the primary refrigerants, and then they are circulated at the place where you need a final cooling effect. Suppose the example is ice plant and air conditioning house or halls. What happens in the case of ice plant? We are preparing ice from the water. Now what happens? Water freezes at 0 degrees Celsius. We cannot supply that much quantity of refrigerant around the cans, because that will be a design problem and that will be not efficient. So then what we do, we prepare the brine, we cool the brine to a desired level, and then we circulate this brine all around the ice cans. So this brine becomes the secondary refrigerants. Brine becomes the secondary refrigerants, and the primary refrigerant will be something else like ammonia or R12, R22, R134, whatever the case may be. In air conditioning system, in some air conditioning, what we do in window type or in split type, what we are using in the house, we have the direct expansion coils and direct cooling effect is generated within the room. But in the big halls, what we do, we are supplying the air. We are supplying the cool air. So this cool air is cooled by, this air is cooled by some refrigerant at some point, and this cool air is supplied to the hall. So this air becomes the secondary refrigerant here, and the primary refrigerant will be something else. So around the evaporator, on the evaporator, we circulate the air, we cool the air on the evaporator, and in the evaporator, we are supplying some primary refrigerant. So these are the differences between primary refrigerant and secondary refrigerants. सेकेंडरी रेफिजेंट्स को हम कूलिंग मीडियम भी बोलते हैं कभी कभी. Chilled water, brines and glycol, these are the secondary refrigerants we are using in the industry. Now, in brine solutions, we have the pure water freezes at 0 degrees Celsius. So we are putting some salt, some sort of salts in the water so that its freezing point decreases. And we have some proportion, a particular amount of salt is added in a particular amount of water. So 100 degree, 100 in 100 kg of water, we are giving somewhere 23 kg of sodium chloride, and this will produce the minimum temperature, and that minimum temperature will be somewhere minus 21 degrees Celsius. So this temperature is known as eutectic point of that freezing of this is known as the eutectic temperature or eutectic point of that brine solution. Similarly, we are using some one more brine is used, water with calcium chloride. So it has 100 kg of water with 29 kg of calcium chloride, and that gives freezing temperature somewhere 51 degrees Celsius. So that 51 is the eutectic temperature of that brine. Now, main challenge is while we are selecting the refrigerant, we have the toxicity, flammability, stability, and atmospheric boiling points. These are the main challenges. We want a refrigerant which should be non-toxic, non-flammable. It should have a good chemical stability, and it must boil between a range of 0 to minus 40 degrees Celsius. These are the challenges while selecting the refrigerants. Common refrigerant we have been using between 1920 to 1930. These refrigerants are ammonia, carbon dioxide, sulfur dioxide, hydrocarbons, methyl chlorides, water. These were the refrigerants we have been using in those days. After 1930 onwards, we have been using the chlorofluorocarbons, synthetic refrigerants, R11, R12, R22, then R507 and others. So we classify the refrigerants in some categories. One classification is the organic refrigerants. Some examples of organic refrigerants are hydrocarbons like methane, ethane, R170 and R50, chlorofluorocarbons, CFCs, hydrofluorocarbons, SCFC, hydrofluorocarbon, HFCs. These are the latest now. This is the latest. Organic, inorganic, water, ammonia and carbon dioxide. This diagram shows the different historical perspective of refrigerants. You can see we start 1834 onwards. इस बीच में जो था कार्बन डाइऑक्साइड, अमोनिया एंड हाइड्रोकार्बन्स वेर यूज्ड. Then 1930s में some chemical compounds in production आया इसमें. क्लोरोफ्लोरोकार्बन्स लाइक R12, R502, then R22 up to 1980s में आया है. इसके बाद से due to ozone depletion some protocols have आया 1987 में Montreal Protocol, which limited and banned the use of high chlorine refrigerants. Then new research came up with R134A, which is latest now used in our ACs and refrigerators. R404A, 410, 407, they have come up. So these are the latest. ये साइकिल है, ब्रीफ साइकिल है रेफ्रिजरेंट्स का, कहाँ से स्टार्ट हुआ और एट प्रेजेंट में क्या है. This chart shows the different consumption of refrigerant in different countries, developing countries, in different fields. तो सबसे ज्यादा आप देखेंगे जो हो रहा है मैक्सिमम 29% इज इन एसी सिंगल स्प्लिट एसीज में, 19% एसी और मल्टी स्प्लिट जो 7 किलोवाट से 2 टन से नीचे का है, 29% सिंगल और स्प्लिट जो 2 टन से नीचे का है उसमें. बाकी सब देखेंगे प्राइवेट फ्रिजेस में 1% है, कॉमर्शियल प्लग इन फ्रिज में 6% है, स्मॉल कंडेंसिंग यूनिट जो 1.5 टन से नीचे का है उसमें 6% है, एंड सो हियर इज हाउ एसी कार एसीज में करीब जो रेफ्रिजरेंट का कंजम्पशन है वो 7% है टोटल कंजम्पशन का. Some of the refrigerants we have, they are the hydrocarbons. ये हाइड्रोकार्बन्स में हालांकि ज़्यादा यूज नहीं है, धीरे धीरे अब यूज स्टार्ट हुआ है, पहले यूज होता था. ड्यू टू फायर हैजार्ड इट वाज छोड़ दिया गया था. नाउ अगेन ड्यू टू द इन्वायरमेंट को लेकर के इसको फिर दोबारा हम यूज करना शुरू कर दिए हैं. सो दिस इज ईथेन, R170, propane, R290, butane, R600, R600A and blends of इसके blends भी हम यूज करते हैं. Then halocarbons. In halocarbon series we have CFCs, HFCs and SCFC and HFCs. So here CFCs में देखिए R11, R12, R113, R114 and R115. These are the chlorofluorocarbons. This is hydrofluorocarbons, R22 and R23. And this is HFC, hydrofluorocarbons. This was hydrofluorochlorocarbons, R122, R22 and R133, R123. प्रॉपर्टी ट्रेंड्स में देखिए कि हाउ दिस डिफरेंट कंस्टिट्यूएंट्स अफेक्ट्स द प्रॉपर्टी ऑफ द रेफ्रिजरेंट्स. मोस्टली आप देखेंगे कि रेफ्रिजरेंट्स में हाइड्रोजन होगा, फ्लोरीन होगा, क्लोरीन होगा, मोस्टली ब्रोमीन होगा. अब इसमें देखिए कि जहां हाइड्रोजन यदि ज्यादा है तो दैट विल बी वेरी हाईली इनफ्लेमेबल। जहां फ्लोरीन ज्यादा है उसका लाइफ टाइम कम है, एटमॉस्फेरिक लाइफ टाइम कम होता है। ठीक है। और ये जो ग्रीन पोर्शन में जो आप देख रहे हैं ये टॉक्सिसिटी आपको डेवलप करता है, जैसे क्लोरीन हो गया, इससे टॉक्सिक है। क्लोरीन एटम आपको क्लोरीन और ब्रोमीन जो है ना ओडीपी कॉज करता है, ओजोन डिप्लेशन का पोटेंशियल इसमें बहुत ज्यादा है। फ्लोरीन को यदि हम ऐड करते हैं इसका ग्लोबल वार्मिंग पोटेंशियल बढ़ जाता है। हाइड्रोजन हाइड्रोजन will increase the flammability and lowers the atmospheric lifetime. So these are the combinations of the different components in the refrigerants. Now the need arose that some refrigerants, few refrigerants or two or more refrigerants can be blended together to achieve differently new properties, which suits us. और इसको जब हम ब्लेंडिंग करते हैं तो डिपेंडिंग अपॉन कि उसकी फ्लेमेबिलिटी क्या होगी, वोलेबिलिटी कैपेसिटी क्या होगी, उसका सुपरहीट डिस्चार्ज सुपरहीट क्या होगा, इसके ऊपर हम उसको ब्लेंडिंग करते हैं। ब्लेंडिंग में दो टाइप के हमारे पास, वी हैव द टू टाइप्स ऑफ blend of refrigerants. One is geotropes and one is azeotropes. Geotropes में what happens, we add up two or more refrigerants which will create a different refrigerant with a different characteristic. But जो नया रेफ्रिजरेंट जो होगा उसका लिक्विड फेस और वेपर फेस में ए है, उसके कंपोजिशन सेम नहीं रहते। व्हेन दे वेपराइज देयर composition is different, when they are liquid their composition is different. This is the problem with the geotropes. Azeotropes are, we are using two or more refrigerants together and a third refrigerant come out which is entirely different from the components. The examples are 500 सीरीज में आता है, 502, 503, ये सब जो है इसके 500, 502, 503, 504 R12 73.8% and 26.2% is R152. इस दोनों को मिलाते हैं तो एक थर्ड रेफ्रिजरेंट बनता है जिसका हमने नाम दिया है 500, R500. नेक्स्ट इज R502, इसमें R22 है 8.8%, ये 8 लिखा हुआ है, सॉरी, दिस इज 48.8% एंड R115 is 51.2%. In R503 we have R23 40.1% and 59.9% is R30. So these are the azeotropes. So a stable mixture, this is the stable mixture having the different property than their mixing components, and they act as a independent refrigerant. Geotropes में क्या है कि a geotropic mixture is one whose composition in the liquid phase differs from that in the vapor phase. Geotropic mixtures therefore do not boil at constant temperature unlike the geotropic refrigerants. Azeotropic mixture, they have, that is a purely third entity having its own properties. But geotropes में क्या होता है कि इसका boiling point fixed नहीं होता है, it has a range of boiling point. It has some band है इसका boiling point का कि उस बीच में वो आपको boil करेगा। बॉयल होने के बाद में जो इसके one component will boil faster, other will boil slower, therefore the vapor phase will be having the different composition. इसके examples है आपके, we have R404, R407, R410 and for R413. We are using R410, ये हम विंडो एसी में यूज करते हैं, जहां R22 का रिप्लेसमेंट है, R34 और R125 को 50-50% में हम इसको ऐड करके R410 लगाते हैं। R407 ये भी हम यूज करते हैं, दैट इज मिक्सचर ऑफ R32, R125 and R134A in the ratio of 23, 25 and 52. So this is geotropic refrigerant. So R410 जो है आपका R22 का रिप्लेसमेंट। R22 will be banned after 2030 world over. R12 is already banned. There is no more R12 component available in the market. No new component. Old component is pass over, that is running, but new component is not being manufactured. That has been completely phased out from the world. Similarly, R22 from complete वर्ल्ड से एक खत्म हो जाएगा R2030 के बाद। We have some thermodynamic properties, physical properties, chemical properties of the refrigerants. So one is the latent heat of evaporation. It is one of the most important property. Higher the latent heat of evaporation, the more the cooling will be available, and less mass flow can be achieved. Therefore, a very compact size can be system can be created. And it's chemically stable. All this chemically stable. That
So,
is,
Sir
yes.
Patrick, sir, if you want, we can go for a break because almost it's 12:37.
फिर ये लंच ब्रेक होगा और
10-15 minutes break, sir.
okay, we will start at 1
Uh,
o'clock,
we can start at 12:50.
12:50.
Yes, 50 because
Okay,
this is an online session. ज़्यादा देर तक break दिया तो
ठीक है, ठीक है, ठीक है, ठीक है,
and you can wind up quickly after that so that we can you can have your
ठीक
lunch
है,
also.
ठीक है, ठीक है, ठीक है,
Okay, sir.
ओके,
Thank
थैंक
you.
यू।
So we are going for a break and we will come back at 12:50 after which the presentation will training will be continued. So all the members, all the experts, all the participants are requested to please join back at 12:50 p.m. Thank you. Sir, shall we start? Patak sir?
जी मैडम आ गया.
Ji sir, I think we can start and then we can complete the second round of training also.
So we were discussing the properties of the refrigerants. So we have some properties, the latent heat of vaporization, chemical stability means latent heat of evaporation should be very high, as high as possible. Chemical stability means within the temperature range of the working cycle, it must not get decomposed. This must be stable. Then it must maintain some safety norms, that is, it should not be flammable, so it must be non-flammable. Then this must be easily available, cheaper in cost, efficiency should be high, and this must be in compatibility with the compressor or lubricants or other material we are using in the system. So these are some of the properties of the refrigerants. Physical property में आता है the physical property like the boiling point, specific volume and all. So this physical property are arranged in the increasing order of the atmospheric boiling point. For air, the boiling point is minus 194.3 degrees Celsius, and for water it is 100 degrees Celsius. So in this order, from minus 194 onwards, we will go up to 100 degrees Celsius in the order in which they are having the boiling temperature. Normal boiling point temperature. This is very important because we must know at what pressure my refrigerant will be operating. Means at what temperature this will boil. So it is higher than the atmospheric or lower than the atmospheric. The selection criteria of the refrigerant for any machine, which refrigerant must be selected for which type of machine. So we have some criteria, that is, one is thermodynamic and thermophysical properties, and second is environmental and safety properties. Under environmental and safety properties, we have some more points: ozone depletion potential, that is ODP, global warming, GWP, and combustibility. Economics of production and maintenance and etc. Means the production cost and maintenance of the machine we are doing, then how cheap or how cost that will be the maintenance. Then suction pressure and discharge pressure. What is the suction pressure of the refrigerant? So the suction pressure should be as higher than the atmospheric. Then discharge pressure should be as low as possible, so that the energy input should be less. The power consumption will be less. In case the discharge pressure is high, then power consumption will be high, and construction cost, material cost will also increase. Next is pressure ratio and compression ratio. The pressure ratio and the compression ratio, this should be low for refrigerant, so that the high volume can be delivered to the system. The latent heat of evaporation should be large possible, so that the required mass flow rate can be reduced. Suppose we have the high latent heat capacity refrigerant, the less quantity will be required for producing the refrigerating effect. इस इक्वेशन को यदि आप देखते हैं तो इसमें हम पाते हैं कि जैसे जैसे हाई latent heat of, from the above equation it can be seen that for a given condenser and evaporator temperature, as the latent heat of evaporation increases, the pressure ratio also increases. So Latent heat of vaporization is must, but it should be, in case it is high, then pressure ratio will be high. So there has to be some optimization somewhere. So there will be some trade-off is required. And toxicity. Toxicity, we are in maintenance or in repairs, we are using, we will be dealing with these components, or while during operation, some manpower, some workers will be operating the machines. So toxicity is of great concern. So ideally, refrigerant should be, in a refrigerant should be non-toxic. और एयर को छोड़ करके कुछ भी ऐसा नहीं है जो कि टॉक्सिक नहीं होता है, सब टॉक्सिक होता है. बट दैट डिपेंड्स अपॉन हाउ कंसंट्रेटेड इट इज इन द एयर और व्हाट इज द एक्सपोजर टाइम विद दैट refrigerants. So toxicity is relative term basically, which means only when the degree of concentration and time of exposure required to produce the harmful effects are specified. So suppose it is highly toxic, थोड़ा एक्सपोजर होगा तो आपको दिक्कत हो जाएगी. कम टॉक्सिक है तो लॉन्गर एक्सपोजर पर भी हमको कुछ नहीं होगा. दैट इज द some fluids are toxic even in small concentrations, and some fluids are mildly toxic. They are dangerous only when the concentration is high and duration of exposure is very long. So toxicity is of much importance. Environmental and safety properties. इसमें हम देखते हैं कि CFC, HFCs are non-toxic when mixed with the air in normal condition. However, when they come in the direct naked flame के यदि अंदर में आता है, even CFCs and HFCs टॉक्सिक हो जाता है and they become explosive. General degree of hazard depends upon, जो hazard है वो डिपेंड होता है कि amount of refrigerant हम कितना, how much quantity of refrigerant we are using, occupancy क्या है, then presence of open flame है कि नहीं जहां हम ऑपरेट कर रहे हैं machines, then order of the refrigerant and maintenance condition. These are the parameters जिसके ऊपर हमारा हजार्ड डिपेंड करता है. फ्लेमेबिलिटी के ऊपर, डिपेंडिंग अपॉन द फ्लेमेबिलिटी ऑफ द रेफ्रिजरेंट्स, द आईएसआर, अमेरिकन सोसाइटी ऑफ हीटिंग एंड रेफ्रिजरेशन एयर कंडीशनिंग जो संस्था है, इन्होंने इसको सेफ्टी ग्रेड में डिवाइड किया है. 6 सेफ्टी ग्रेड्स है, A1 to A3 and B1 to B3. So A1 group is the least hazardous and B3 group is the most hazardous. तो जितने भी आपके CFC जो हैं, they come under the A1 group, और ये जो आपको 1100 सीरीज के जितने भी रेफ्रिजरेंट्स हैं, they come under B3 groups. Then economic properties, it should be very cheap, inexpensive and easily available in the market. So these are the property requirements of. हम आप हैं nomenclature के ऊपर, how the name or trade name is given, or coding is how the coding is given to the refrigerants. Refrigerants are basically given, they are replaced with the कोई भी जो रेफ्रिजरेंट है, हम उसको R लेटर के साथ हम उसको प्रोसीड करते हैं. R डिपेंड्स, R shows the refrigerant. देन इसके बाद में हम कोई नंबर देते हैं, लाइक R12. So how this R12 has come, or R22, R22, ये कैसे आया है? We will discuss this with some examples. Let's see. लेटर आर जो होता है, ये इंडिकेट्स करता है कि दिस इज फॉर रेफ्रिजरेंट. अब इसमें देखेंगे जो मीथेन बेस्ड रेफ्रिजरेंट्स है वो 0 सीरीज में स्टार्ट होता है. फिर जो प्रोपेन बेस्ड है उसमें 1 से स्टार्ट होता है. जो साइक्लिक ऑर्गेनिक कंपाउंड है 200 सीरीज में स्टार्ट होता है, एंड सो ऑन. अलग अलग इसके सीरीज दिए हुए. हाउ द नोमेनक्लेचर्स आर गिवन. Now here we have most of the refrigerants we are having from methane or ethane based. So methane is CH4 and ethane is C2H6. इसी में क्या करते हैं हम कि हाइड्रोजन कंपोनेंट्स को रिप्लेस करते हैं फ्लोरीन से या क्लोरीन से और उसको हम नाम देते हैं. तो वी विल हैव, इसका नाम जो होगा सपोज दैट इज RXYZ, where X indicates something, Y indicates something, Z indicates something. What this something is? X plus 1 indicates the number of carbon atoms. किसी भी कंपोनेंट्स रेफ्रिजरेंट्स में जो लेटर है X वो इंडिकेट करता है X plus 1 is the carbon atom, Y minus 1 is the hydrogen atom, and Z is the number of fluorine atoms. और जो बैलेंस बच जाता है इसको केमिकली बैलेंस करने के लिए जो भी आपको आएगा दैट विल बी द क्लोरीन एटम्स. कभी कभी होता है टू डिजिट्स के भी आपको मिलेंगे. 2 डिजिट्स का जो रेफ्रिजरेंट है लाइक यहाँ पर आपका 0 है बिकॉज 3rd डिजिट इज 0. तो 0 को नॉर्मली हम लिखते नहीं है. अब हाउ दिस R12 हैज कम, वी विल टेक अप दिस एग्जांपल. R22 का आप एक एग्जांपल ले लीजिए. R22 में कैसे आया है. नाउ हियर द फर्स्ट लेटर इज X इज 0. ये दो डिजिट का है, 3 डिजिट का होना चाहिए XYZ. इसमें Y है, Z है, X नहीं है. X नहीं है इसका मतलब X 0 है. X इज 0. द नंबर ऑफ कार्बन आइटम 0 plus 1. उसके बाद ये जो 2 जो आया है नेक्स्ट Y जो आया है, दिस Y इज नंबर ऑफ हाइड्रोजन एटम्स. इसमें हाइड्रोजन एटम्स कितने होंगे? 2 minus 1. 1 इसमें हाइड्रोजन एटम्स होंगे. और Z जो है ना, ये जो कंपोनेंट है दिस इज इक्वल टू नंबर ऑफ फ्लोरीन एटम्स. तो इसको बैलेंस करने के लिए, CH4 को बैलेंस करने के लिए यदि आप इसको देखें तो C के साथ 4 हाइड्रोजन चाहिए. 1 हाइड्रोजन तो हमारे पास है, 2 फ्लोरीन है. अब एक और चाहिए तो थर्ड, वो जो चौथा जो होगा वो क्लोरीन हो जाएगा. जो बाकी जो बच जाएगा दैट विल बी द क्लोरीन. सो बैलेंस इज 4 minus 1 minus 2 is that is 1. 1 is the number of chlorine. So केमिकल फॉर्मूला इसका आ जाता है R22. दैट इज एक इसमें कार्बन है, एक हाइड्रोजन है, एक क्लोरीन है और 2 फ्लोरीन है, CHClF2. तो दिस इज मोनोक्लोरो डाइफ्लोरो मीथेन. इस ढंग से वी आर गिविंग द नोमेनक्लेचर टू द रेफ्रिजरेंट्स. इसमें आप देखेंगे अब कुछ इनऑर्गेनिक कंपोनेंट्स हैं हमारे पास लाइक वाटर, अमोनिया, कार्बन डाइऑक्साइड, सल्फर डाइऑक्साइड. इस रेफ्रिजरेंट को हमने 700 सीरीज में डाल दिया. R717. नाउ 17 इज द मोलिकुलर वेट ऑफ अमोनिया और इसके पहले हमने 7 सीरीज डाल दिया. 44 इज द मोलिकुलर वेट ऑफ कार्बन डाइऑक्साइड. 744 इज R74. It has come like that. Same way water, 18 is the molecular weight of water. So 718 is the nomenclature of water and so on. अब इस पूरे को ये देखें how their nomenclature, how the nomenclature is given. जो भी आपको मिलता है 2 डिजिट का या 3 डिजिट का या 4 डिजिट्स का, how we can give the nomenclature. So ये यहाँ पर देखिए, the first digit on the right number of the number is number of fluorine atoms. R22 में जो right का जो 2 है that is fluorine atoms. The second digit from the right is 1 more than the number of hydrogen atoms. जो second digit होगा right से, जो भी हाइड्रोजन का आइटम है उसमें आप 1 जोड़ दीजिए. सो दैट विल गिव यू द नंबर ऑफ सेकेंड डिजिट का जो सेकेंड पोजीशन का जो डिजिट होगा दैट यू विल गेट. R22 में आप देखिएगा कि हाइड्रोजन आइटम 1 है, 1 + 1 2 आ जाएगा. थर्ड डिजिट फ्रॉम द राइट इज 1 लेस देन द नंबर ऑफ कार्बन आइटम. जितना भी कार्बन आइटम है उससे एक कम करके हम देते हैं थर्ड डिजिट को। जैसे R22 में थर्ड डिजिट 0 है, 0 जो हुआ 1 - 1 इज 0, तो यहाँ पर एक कम करके इसको लिखते हैं। सो दैट इज व्हेन दिस डिजिट इज 0, फिर हम उस यदि 0 आ गया वो डिजिट तो हम वहाँ पर उस नंबर को हम ओमिट कर देते हैं। R22 में या R12 में थर्ड डिजिट 0 थी, इसलिए हम वहाँ पर 0 नहीं लिखते हैं, सिंपली R12 या R22 लिखते हैं। फोर्थ डिजिट फ्रॉम द राइट is equal to the number of unsaturated carbon bonds in the compound. When this, इसमें भी यदि 0 है तो फिर हम इसको 0 डालते हैं। इस ढंग से यदि 4 डिजिट्स में आपको नोमेनक्लेचर यदि मिलता है तो क्या होगा, व्हाट द राइट मोस्ट क्या बतलाता है, उससे पहले वाला क्या बताता है, एंड व्हाट नेक्स्ट। सो दैट वे वी आर गिविंग द नोमेनक्लेचर ऑफ द आइटम्स। Number of chlorine item is found by subtracting the sum of the fluorines, bromines, if present, hydrogen atoms from the total number that can be attached to the carbon. कार्बन बॉन्ड को उस कंपाउंड को फिक्स करने के लिए जितने भी चाहिए, तो आपको फ्लोरीन मिल गया, हाइड्रोजन मिल गया, ये सब मिल गए, तो क्लोरीन आइटम कितना होगा, तो टोटल नंबर ऑफ आइटम्स रिक्वायर्ड टू बैलेंस द इक्वेशन माइनस दिस सम इज इक्वल टू द नंबर ऑफ क्लोरीन एटम्स। किसी किसी केस में क्लोरीन नहीं होता है, ब्रोमीन होता है। किसी किसी कंपाउंड में, किसी किसी रेफ्रिजरेंट में ब्रोमीन होता है, तो वहां पर हम एक बी लेटर लिख करके ब्रोमीन को हम रिप्रेजेंट करें, वहां पर हम बी लिखते हैं। जो ब्लेंड वाले हैं, जियोट्रोप्स एंड एजियोट्रोप्स, तो जो जियोट्रोप्स हैं दे आर कमिंग इन 400 सीरीज। जैसे 400 सीरीज में आपको 410, 407, 401 ये सब जो है आपको जियोट्रोप्स है। जो एजियोट्रोप्स है उसको हम 500 सीरीज में डालते हैं, एजियोट्रोप्स को 500 सीरीज में डालते हैं। सीरीज में आपको एजियोट्रोप्स को, जैसे 501, 502, 503, 504 दे आर द एजियोट्रोप रेफ्रिजरेंट्स। जो हाइड्रोकार्बन्स हैं दे आर गिवन, ऑर्गेनिक कंपाउंड्स जो आता है दे आर गिवन 600 सीरीज। 700 सीरीज में बता दिया हूँ कि नॉन ऑर्गेनिक कंपाउंड्स के लिए है, एंड सो ऑन। यदि दो के मोलिकुलर मास यदि एक ही आ जाता है तो फिर वहां पर हम अलग अलग दोनों का, किसी को ए कैपिटल लेटर देते हैं, किसी को बी कैपिटल देते हैं, किसी को सी कैपिटल, एंड सो। जो 1000 सीरीज है वो आपका अनसैचुरेटेड ऑर्गेनिक कंपाउंड्स के लिए हम 1000 सीरीज यूज करते हैं। सो दिस वे वी आर गिविंग द नोमेनक्लेचर टू द refrigerants. In case you have any question on this refrigeration and refrigerant, you can ask me. Otherwise, we will move to the next topic, that is psychometrics.
So the participants are requested to kindly ask any questions, put it on the chat box so that I can place it to the expert. Meanwhile, sir, you can continue. If the questions will come, I will let you know.
Okay. Thank you. Now, the next, we have the next topic, psychometry. And this psychometry study is required for air conditioning. And air conditioning में आप देखेंगे कि we have combination as well as psychometry. These two, इस दोनों को कंबाइन करते हैं तब जाकर के हमारा एयर कंडीशनिंग होता है। इन एयर कंडीशनिंग, अब इस लेक्चर में हम देखेंगे कि एटमॉस्फेयर के बारे में, थोड़ा सा एयर के बारे में हम समझेंगे, उसके जो डिफरेंट टर्म्स है उसके बारे में समझेंगे, और जो साइकोमेट्रिक है, व्हाट द साइकोमेट्री इज एंड व्हाट आर द डिफरेंट साइकोमेट्रिक प्रोसेसेस वी डू इन द एयर कंडीशनिंग सिस्टम। We all know the air we have, they are all around our us in the atmosphere. Air has two temperatures. One is the drivable temperature and one is the wettable temperature. And it has some moisture presence in this. So that moisture presence is known as the humidity or absolute humidity. And one more term comes the relative humidity. Then we will be using psychometric charts. चार्ट्स में हम देखेंगे कि उसका कैसे हम रीड करते हैं, and what are the different properties we can read from the charts. Then we will be discussing some human comforts, how the air conditioning, what are the factors which affects the human comforts. Atmosphere में, the atmosphere we have the total pressure. This total pressure is sum of the dry air and the water vapor. जो एटमोस्फेयर में जो वाटर वेपर्स है उसका प्रेशर क्या है प्लस जो ड्राई एयर है उसका प्रेशर क्या है, इस दोनों प्रेशर को यदि हम करें तो फिर दिस सम बिकम्स द टोटल प्रेशर ऑफ द एटमोस्फेयर और एनी सैंपल ऑफ द एयर. In psychometry, when we discuss the properties of the air, we have the three temperatures. One is the drivable temperature, one is the wettable temperature, and one is the dew point temperature. Drivable temperature is when we are using a thermometer whose bulb is dry and it is stationary in the air, then whatever temperature we read or record, that is known as the drivable temperature. Wettable temperature is when you measure the temperature of the air with a thermometer whose bulb is wet with the pure water and the thermometer moves in the air at some certain speed. Then the temperature recorded will be known as the wettable temperature. और इस दोनों टेम्परेचर का जो डिफरेंस होता है उसको हम बोलते हैं वेटेबल डिप्रेशन. एक थर्ड टेम्परेचर है ड्यू पॉइंट टेम्परेचर. ड्यू पॉइंट टेम्परेचर में क्या है कि इसको यदि हम टीएस डायग्राम पे देखें, तो इस एयर का मान लो कि एयर जो हमारे पास है सुपर हीटेड रीजन में है. इन केस वी कूल डाउन द एयर at constant pressure, then a point will come when the first water droplet will come out from the air, and the moment it comes down, at the time what is the temperature of the air, that temperature is known as the dew point temperature. So this is nothing but the condensation point of air when the first droplet of water comes. So when the air is saturated, और उस टाइम में क्या होगा कि जो एयर में जितना मॉइस्चर होना चाहिए उस सैंपल में, दैट मच मैक्सिमम mass of the moisture will be available in that air. So that is the air will be saturated. So temperature of the saturated air can be defined as the dew point temperature. एक आता है एब्सोल्यूट ह्यूमिडिटी. एब्सोल्यूट ह्यूमिडिटी बोलते हैं द मास ऑफ वाटर वेपर प्रेजेंट इन यूनिट मास ऑफ द ड्राई एयर. जो भी आपका एयर का सैंपल है उसमें ड्राई एयर है, तो ड्राई एयर है 1 kg ड्राई एयर में हाउ मच क्वांटिटी ऑफ वाटर वेपर इज अवेलेबल, दैट इज नोन एज द एब्सोल्यूट ह्यूमिडिटी. इसको मैथमेटिकली हम इसको ऐसे लिखते हैं ओमेगा, दैट इज mv अपॉन ma, और इसका जो आता है फाइनली the 0.622 pb upon pa, where is the pb is the partial pressure of the water vapor and pa is the partial pressure of the dry air. What is the relative humidity? We all know how much water vapor is present in a sample of air at a particular temperature and how much maximum water vapor it can hold at the same temperature. इस दोनों का जो रेशियो होता है, that ratio is known as the relative humidity. Lower the relative humidity, more the water vapor the air can absorb. Higher the relative humidity, less the water vapor the air can absorb. एब्सोल्यूट ह्यूमिडिटी हम बोलते हैं कि जो भी मास आपका वाटर वेपर है अवेलेबल प्रेजेंट है एयर में, दैट क्वांटिटी इज नोन एज एब्सोल्यूट ह्यूमिडिटी। रिलेटिव ह्यूमिडिटी मैं बता दिया हूँ, एब्सोल्यूट ह्यूमिडिटी डिवाइडेड बाई सैचुरेटेड ह्यूमिडिटी मल्टीप्लाइड बाई 100, इसको हम RH परसेंटेज में लिखते हैं। ड्राइवल टेम्परेचर वी हैव ऑलरेडी डिस्कस्ड। यह आपका ड्राइवल टेम्परेचर का, इस थर्मोमीटर से जो भी आप टेम्परेचर लेंगे दैट इज अ ड्राइवल। वेट बल्ब में है कि इसका जो बल्ब है इट इज विक विद प्योर वाटर, और वेट बल्ब टेम्परेचर हमेशा ड्राइवल टेम्परेचर से कम होता है। व्हेन द एयर इज सैचुरेटेड, उस समय में जाकर के बोथ द टेम्परेचर विल बी सेम। वेटेबल टेम्परेचर और ड्राइवल टेम्परेचर का जो डिफरेंस होता है उसको हम बोलते हैं वेटेबल डिप्रेशन। वेटेबल डिप्रेशन ये इंडिकेट करता है, सपोज द वेटेबल डिप्रेशन इज वेरी हाई, इट मींस इट शोज दैट द moisture content in the air is less. Therefore, the more quantity of air can be, the water can be injected into the air, and the air temperature can be brought down. So, like in the desert condition where the water particles in the atmosphere is very less, so that air is dry. लेकिन जो ट्रॉपिकल रीजन है या हाई ह्यूमिड एरियाज है लाइक आसाम और कोस्टल एरिया है लाइक बॉम्बे, तो वहां पर ह्यूमिडिटी ज्यादा होती है, तो वहां पर आपको वेट बल्ब डिप्रेशन आपको कम होगा। One more property is the specific enthalpy. The enthalpy of unit mass of the dry air is known as enthalpy. Enthalpy means the total heat content of that air. A specific volume, unit mass of the air, how much volume it occupies, that is the specific volume of the air. और इस सारा का सारा प्रॉपर्टी हम साइकोमेट्रिक चार्ट के ऊपर हम इसको रीड आउट कर सकते हैं। अब ये देखिए साइकोमेट्रिक चार्ट है हमारे, ये आप सबको पता होगा। तो इस चार्ट के ऊपर जो हॉरिजॉन्टल लाइन है ड्राई है, वर्टिकल लाइन राइट साइड में आपको स्पेसिफिक ह्यूमिडिटी देता है, कर्व लाइन जो है आपका रिलेटिव ह्यूमिडिटी देता है। लाइक ये जो तिरछा लाइन जो देख रहे हैं इंक्लाइंड लाइन, दिस गिव्स द स्पेसिफिक enthalpy line or vegetable temperature line. So these are the different lines which we can read on the psychometric chart and find out the different properties of the air. Psychometric chart का पढ़ने का तरीका I think most of you might be knowing. We will not discuss on this point much. Reading a psychometric chart, same. Suppose the dry bulb temperature is given and wet bulb temperature is given. Then we locate a point on the psychometric chart. Suppose this is the dry bulb temperature, so we'll go vertically down, and this is the wet bulb temperature. Suppose particular 25 degree. So this is the 25 degree wet bulb temperature line. Where it cuts, that point is the air will be marked on the psychometric chart, and the different lines passing through that point will indicate the different property. This is the relative RH लाइन है यहाँ पर, यहाँ से स्पेसिफिक वॉल्यूम लाइन क्या होगा, ये आपका स्पेसिफिक ह्यूमिडिटी लाइन जा रही है जो कि राइट साइड में जहां भी कट करेगा, सो दैट वी कैन फाइंड आउट द स्पेसिफिक ह्यूमिडिटी. सो डिफरेंट प्रॉपर्टीज वी कैन फाइंड आउट फ्रॉम दिस साइकोमेट्रिक चार्ट with the help of the psychometric chart. Just by knowing the any two properties, we can find the remaining property of the air from the psychometric chart. अब इसी पर देखिए आप, ये है आपको कांस्टेंट वॉल्यूम लाइन दिखलाता है, ये आपको कांस्टेंट एंथैल्पी लाइन दिखलाता है, ये आपको ड्राई बल्ब टेम्परेचर, ये आपको वेट बल्ब टेम्परेचर लाइन दिखलाता है. वेट बल्ब टेम्परेचर लाइन नॉर्मल and constant enthalpy line both pass through the same line. Minor deviation is ignored for academic purpose. This curved line, this indicates the relative humidity lines. तो ह्यूमन कंफर्ट में हम डिफाइन करते हैं कि दैट कंडीशन इन एनी स्पेस at which the majority of the people feel very comfortable to their desire. Means, suppose in a room कि द रूम हैज ए पर्टिकुलर टेम्परेचर एंड पर्टिकुलर ह्यूमिडिटी, रिलेटिव ह्यूमिडिटी, और उस पर कितना मैक्सिमम लोग कंफर्टेबल फील करते हैं, उसको हम बोलते हैं कि ये इनका कंफर्ट लेवल है। एंड जो एसरे ने जो दिया है वो कंफर्ट लेवल, उसका रेंज है 22 डिग्री टू 26 डिग्री डाइवल टेम्परेचर एंड 40 to 60 डिग्री 60% RH. So between this range, majority of the people from the different part of the world, they feel very comfortable and they enjoy working and occupancy of that environment. ह्यूमन कंफर्ट में आप देखेंगे कंफर्ट लेवल, इसमें आप देखिए तो यदि अलग अलग एक्टिविटी है तो अलग अलग एक्टिविटी में अलग अलग आपका उसका कंफर्ट लेवल चेंज होता है। वन एग्जांपल इज सीटेड एट रेस्ट, थिएटर या होटल में, तो वहां पर जो टोटल हीट आपको चाहिए, सेंसिबल हीट 90 और 25 आपका है लैटेंट हीट। उसी में यदि 20 डिग्री सेंटीग्रेड आपका टेम्परेचर है, माने ड्राइवल टेम्परेचर है, उसी में ड्राइवल टेम्परेचर 22 डिग्री हो जाता है, उसमें सेंसिबल हीटिंग उसकी 80 का है और लेटेंट हीट 35 है, एंड सो ऑन। सो दिस इज द ग्राफ ऑफ डिफरेंट लेवल ऑफ डिग्री ऑफ एक्टिविटी, कहाँ कहाँ ये सब होता है, और डिपेंडिंग अपॉन कि अलग अलग जगह में अलग अलग आपको सेंसिबल हीट, लेटेंट हीट, लोड डिफर करता है डिपेंडिंग अपॉन कि इन्वायरमेंट कंडीशंस क्या है। ह्यूमन कंफर्ट को जो मोस्टली जो अफेक्ट करता है दैट इज द टेम्परेचर। वो टेम्परेचर से आपको पता लग जाएगा कि यू फील सेंसेशन ऑफ कंफर्ट और डिस्कम्फर्ट। सेकेंड पैरामीटर इज द relative humidity. Third parameter is the quality of air in the conditioned space. And fourth parameter is the speed at which the air is coming in the space. So जो टेम्परेचर है वो आपको 22 से 27 डिग्री यहाँ पर दिया हुआ है, 22 से 27 डिग्री सेल्सियस, दिस इज द टेम्परेचर रेंज। इस पर मेजॉरिटी ऑफ द पीपल फील वेरी कंफर्टेबल। रिलेटिव ह्यूमिडिटी इज 40 to 60%, एंड जो वेलोसिटी होना चाहिए 15 मीटर पर मिनट, और जो क्वालिटी ऑफ एयर होना चाहिए दैट एयर मस्ट बी फ्री फ्रॉम एनी डर्ट, डस्ट, फ्यूम्स, एनी पैथोजेंस, बैक्टीरिया, वायरस एटसेट्रा। सो दैट मस्ट बी प्योर एयर। देन दिस रेंज इज द कंफर्ट जोन रेंज, आपका 22 से 27 टेम्परेचर, 40 to 50 डिग्री RH, 15 मीटर पर मिनट वेलोसिटी एंड प्योर एयर। अदर फैक्टर्स जो अफेक्ट करता है कंफर्ट को, सपोज यू आर ऑक्युपाइंग ए स्पेस, उस स्पेस में ऑक्युपेंसी क्या है और कितने लोग वहां पर हैं, डिपेंडिंग अपॉन दैट जो फ्रेश एयर आपको उसमें चाहिए, क्योंकि फ्रेश एयर यदि नहीं है तो ऑक्युपेंसी के कारण देयर विल बी मच मोर रिलीज ऑफ CO2 एंड human orders will be also dissipated from the bodies, and that will give a discomfort. So to avoid this, a fresh air is must, and it is recommended that 6 to 8 liters per second per occupant fresh air must be supplied in a air conditioned room. डिग्री ऑफ कंफर्ट डिफर्स फ्रॉम पर्सन टू पर्सन, लेकिन इसमें जो मेजॉरिटी जो इंजॉय करता है इस पैरामीटर को दिया। अब देखिए एक केस है, वार्म एंड ह्यूमिड क्लाइमेट, जैसे बॉम्बे का एग्जांपल है आपका यहाँ पर। बॉम्बे का एक एग्जांपल है जिसमें देखिए कि the temperature is almost 35 degrees Celsius, and हमको रेंज क्या चाहिए, 22 से 27 डिग्री का चाहिए, और 40 से 60 डिग्री का आपको रिलेटिव ह्यूमिडिटी चाहिए। तो ये जो ग्रीन जो आपका जोन बन रहा है, दिस इज द कंफर्ट जोन। अब इस जोन में आने के लिए ये जो एयर होगा, इस एयर को हम कूल करेंगे। कूलिंग करने के बाद इसको इतना कूल करेंगे कि इसमें से जो एक्सेस मॉइस्चर है वो निकल जाए, और फिर जा करके सप्लाई कंडीशंस को ये सेटिस्फाई करें। सो यहाँ पर जो वो होगी, यहाँ पर होगा डिह्यूमिडिफिकेशन लैटेंट हीट, हम डिह्यूमिडिफाई करेंगे इसको, इसमें से मॉइस्चर्स को निकालेंगे। सो एक लोड होगा, डिह्यूमिडिफिकेशन लोड होगा, और इसके वेटेबल ड्राइबल टेम्परेचर को हम रिड्यूस करेंगे तो सेंसिबल लोड। इस पर दो लोड आपको आते हैं, एक हॉरिजॉन्टल जो है आपको सेंसिबल लोड है, और जो वर्टिकल है दैट इज द लेटेंट हीट लोड। दिस केस ऑफ सेम मुंबई का ही है। अब इसी जोन में आने के लिए हम क्या कर सकते हैं, ये प्रोसेस दिया है कि यहाँ से एयर ले करके इसको हम रिड्यूस करेंगे इसके टेम्परेचर को। जब टेम्परेचर रिड्यूस कर देंगे, वी हैव टू रिड्यूस द टेम्परेचर सो दैट द एक्सेस मॉइस्चर फ्रॉम द एयर कम्स आउट, and for that you will have to maintain the temperature of the cooling coil less than the apparatus dew point, so that the temperature is less than the dew point temperature. Then that air is supplied to the room, but that will be too much hot air, so therefore we will have to bit heat it up. So on the way, so यहाँ पर क्या होगा कि दो काम होगा, एक तो आप सेंसिबल कूलिंग करेंगे, फिर डिह्यूमिडिफिकेशन करेंगे, फिर इसको हीटिंग करेंगे। इसका सेंसिबल हीट लोड भी इस पर आएगा और लेटेंट हीट लोड भी इस पर। एक लद्दाख का कंडीशन है, एक आप इसको देखिए, ड्राई इलाका है लद्दाख, where humidity is very less, temperature is very low. So temperature is 15 degrees Celsius, suppose, and we want to maintain a temperature of 22 to 27 degrees Celsius. So we have to go into this range, and relative humidity here is somewhere 10%. So we have to increase the relative humidity to 40 to 60%. So ये बन जाता है कंफर्ट जोन। यहाँ पर जाने के लिए क्या करना पड़ेगा, we will have to heat the air first, and then in the hot air we will have to inject the water. We will have to inject the water, so that quality of air will be satisfying this comfort zone requirement. So this is the case of the dry atmosphere. सेम राजस्थान में विंटर सीजन का भी कंडीशन यहीं से मिलता जुलता है। अब आते हैं साइकोमेट्रिक प्रोसेस में। ये सब हमने देखा कि हाउ इट इज डन। सो इन साइकोमेट्रिक प्रोसेस इन एयर कंडीशनिंग वी हैव the temperature controls, then we have the humidity controls, then we mix up the two or more streams of the air. So what we do the cooling, we do the heating, we do the humidification, we do the dehumidification, then we mix up the two different air streams. So these are the different processes which we perform in the air conditioning. अब देखिए एयर कंडीशनिंग में जो प्रोसेस है टेम्परेचर कंट्रोल में क्या करते हैं, one is the sensible heating और एक है sensible cooling. So when we heat the air at constant specific heat, then this is known as sensible heating. So ये जो कंडीशन होगा, मान लो कि यहाँ पर एयर का कंडीशन है, if we heat to right side, temperature is drivable temperature is increasing, specific humidity remains constant. Same way in case you cool, the drivable temperature will decrease, specific humidity will remain constant. So this is known as the sensible cooling or sensible heating. Next is humidification control. So हम इसी ईयर में यदि हम मॉइस्चर ज्यादा ऐड करें, once you add the moisture, the specific humidity will increase, so it will be a vertical line, and when you condense or when you remove the moisture from this, then a specific humidity will fall down. So this is the vertical line here. So this is humidification and this is dehumidification. One more process is heating and humidification, and this is cooling and dehumidification. So heating and humidification में क्या करते हैं कि एयर को हम हीट भी करते हैं और ह्यूमिडिफाई भी करते हैं। इस दोनों आप ये वर्टिकल लाइन है और ये है, यहाँ से आप हाइपोटेनस यदि आप ले लें इसके बीच से, so that path shows you have to increase the moisture and you have to increase the temperature also. So this is known as heating and humidification. इसका जो जस्ट जो उल्टा होगा, रिवर्स हो, that will be cooling and dehumidification. So in cooling and in dehumidification, B, remove the moisture, and B, reduce the heat temperature. For designing any air conditioner, we have the heat loads, sensible heat loads, and latent heat load. And one is the sensible heat factor. So, what is the total sensible heat on the system? And what is the total latent heat of the system? So, sensible heat divided by sensible heat and latent heat is known as sensible heat factor. इस फैक्टर को हम यूज करते हैं एयर कंडीशनिंग को डिजाइन करने के लिए. कोई एग्जाम्पल से मैं आपको आगे बताऊंगा कि हाउ इट इज डन. Let us see the temperature control. When you increase the temperature, when you heat the air, while you are heating the air, see on the psychometric chart, the initial condition is here. When you heat, final condition is here. What is changing is the relative humidity is decreasing, dry bulb temperature is increasing, specific volume is increasing, specific enthalpy is increasing. So this parameter ये आपको चेंज होता है. इसी को यदि आप कूल करते हैं तो जस्ट इसका रिवर्स हो जाएगा. When you do the sensible cooling, what will happen? The relative humidity will increase, temperature, dry bulb temperature will decrease, specific enthalpy will decrease, specific volume will decrease. So these are the processes happening on sensible heating or on sensible cooling. ये आपका sensible cooling का है. क्या क्या होगा ये मैं इसमें बता दिया था. Now sometimes we mix up the two air stream. Practically we do this. We take part of the air, we are taking fresh air from the atmosphere, and part of the air we are taking from the return path of the air conditioner. We mix it and then we supply to the cooling coil where it is conditioned. Then we are supplying to the room. So this is the mixing of the two air streams. Suppose outside air condition is this A, then inside condition is B, and they are mixed up in some ratio. Suppose 3:4. So 3 part आपको 1:4 में आप कर लीजिए. जैसे 1 पार्ट आपका बाहर का एयर है और 4 पार्ट आपका अंदर का एयर है. तो जो रिजल्टेंट जो आपको मिलेगा, जो कंडीशन जो मिक्सचर का जो कंडीशन मिलेगा, इसी लाइन के ऊपर जो आपका रूम का जो कंडीशन है उसके आसपास मिलेगा इन दैट रेशियो. यहाँ से यहाँ के लाइन को हम 5 इक्वल पार्ट्स में डिवाइड कर देंगे और जो राइट साइड से जो आउटसाइड कंडीशन से वहां से 4 पॉइंट्स इसी पर आएंगे. तो दिस 4th पॉइंट विल बी द आउटलेट कंडीशन ऑफ द मिक्सिंग ऑफ द एयर. जैसे आप यहाँ पर देखिए, यहाँ से हम फ्रेश एयर लेते हैं, यहाँ से हम रिटर्न एयर लेते हैं, दोनों को यहाँ पर मिक्सअप करते हैं और 1 में यहाँ पर आपको मिला. इस एयर को हम सप्लाई करते हैं कहाँ पर? कूलिंग कॉइल में या हीटिंग कॉइल में, डिपेंडिंग अपॉन माय रिक्वायरमेंट. एंड दिस कैन बी 2 is the outside condition, 1 is the inside condition, and we are mixing in some ratio. So resultant is the 3rd point. अब इसको साइकोमेट्रिक चार्ट के ऊपर हम इसको लोकेट कर सकते हैं कि आउटसाइड का कंडीशन क्या है, इनसाइड का कंडीशन क्या है, एंड इन विच रेशियो यू आर मिक्सिंग द एयर. सो दैट वे यू कैन फाइंड आउट द 3rd पोजीशन. और जब आपका 3rd पोजीशन मिल गया, व्हेन यू गेट द 3rd पोजीशन, you can find out the remaining property of this air from the psychometric chart. So इसमें यदि आप देखेंगे तो मास फ्लो रेट, यहाँ क्लास ले रही है. सो मास ऑफ द एयर में देखेंगे मास फ्लो रेट में. सो MA क्वांटिटी ऑफ दिस एंड MA2 क्वांटिटी आपका दूसरा मिल रहा है. ये दोनों मिलकर के MA3 क्वांटिटी आपका मास ऑफ द एयर यहां से निकल. सेम वे इसकी आप specific humidity of this will be a specific humidity of, आप इस इक्वेशन से आप लगा सकते हैं W1 इंटू MA1 प्लस W2 इंटू MA2 इज इक्वल टू W3 इंटू MA3. सो ये आपका कंटिन्यूटी इक्वेशन से आपको यहाँ पर आपको पता लगता है. सेम एनर्जी इक्वेशन यदि आप लें तो enthalpy of this air plus enthalpy of this air multiplied by the mass flow rate will be the enthalpy of this air, specific enthalpy of this air multiplied by the mass of this one. So that way you can find out mathematically also. Plus here आप ग्राफ से चार्ट से आप डायरेक्टली आप निकाल सकते हैं. Adiabatic mixing of the air streams. इसमें देखें, एक है adiabatic saturation कि how to humidify the air adiabatically. This is the case of the desert air cooler. Desert air cooler we are using. So in desert air cooler, what we do, we are taking the air stream from outside, we are passing on the air on the water surface from the three sides. So this is the water tank, this is the pump. यहाँ से हम इसको पंप को ले जाकर के क्या करते हैं कि यहाँ से स्प्रे करते हैं. And this will be insulated. This will be completely insulated. यहाँ पर दिखलाया नहीं है insulation. So this will be completely insulated. So what happens? The air which is coming from the atmosphere, that is unsaturated air, when it is coming in contact with the water vapors, part of the water vapor will evaporate. Part of the water particles from the surface will evaporate and this will join the air stream. In doing so, what happens? The temperature of the water decreases. Temperature of the water decreases. Also, the temperature of the air also decreases, because for evaporation of water, we need latent heat. This latent heat comes part from the air stream and part from the water particles at the bottom of the air itself. So what happens? Water is losing the heat for its own evaporation. Therefore, the water will come in, the water temperature will fall down. And while doing so, there is no external heat. बाहर से कोई heat नहीं आ रहा है और system का heat बाहर भी नहीं जा रहा है. So this is a completely adiabatic process. और ऐसे process को हम बोलते हैं adiabatic saturation process. And this is shown on the psychometric chart by this. So ये आपका A point है. A point पे हमने इस moisture add करना शुरू हुआ. इसकी enthalpy change नहीं होती है. Enthalpy remains same. Total heat content remains same because the water is losing the heat, air is also losing the heat, but यहाँ पे आकर के दोनों मिल जाता है. वो जो heat lose होता है, that is just only for evaporation purpose and for nothing else. Therefore, such a process is known as adiabatic saturation process. और ये process हमारा desert air cooler में होता है. The same steam injection, we can humidify the air and we can heat the air. Means heating and humidification can be done by supplying the steam into the air stream so that the air stream will get heated up. At the same time, some particle of the steam will get evaporated and that will mix up with the air particles. So air humidity will increase, and this is shown as like this on the psychometric chart from this dot to this dot. Now air washer by chilled water means cooling and dehumidification. This is cooling and dehumidification. So what happens here, in case we have the water available at a temperature less than the dew point temperature of the air, if such water is passed through air stream, what will happen? The air will lose its water particle into the air and its temperature will be falling down and condensation will also take place. So आप यहाँ से देखिए A point यहाँ पर है और C point यहाँ पर है. So here the dival temperature has decreased. At the same time, the specific humidity has also decreased. So this is cooling and dehumidification. This cooling and dehumidification can be also done on the cooling coil. This is, ये जो coil आप देख रहे हैं, this coil is of any chiller. ये chiller का coil है. इसके अंदर से chilled water or chilled refrigerant is flowing through this, and over this we can circulate air stream. Now the surface temperature of this coil is maintained at lower temperature than the dew point temperature of the air. What will happen? When the air will pass over the surface, the excess quantity of moisture will condense, and that will result into cooling of the air and dehumidification. So this we are doing practically in air conditioning window type or split type or central AC type. This is the apparatus is used there. Now multi-step process में क्या होता है कि simultaneously different processes are taking place simultaneously. Means cooling भी हो रही है, condensation भी हो रहा है, and heating भी हो रही है. So we have some cooling and humidification followed by reheating. So simultaneously, suppose in winter season the specific humidity is very, very less, and we want to maintain the relative humidity between 40 and 50, 40 and 60. Then what we do first, we cool the air. Sorry, this is different. This cooling, dehumidification, and reheating. In air conditioning, what we do? Suppose we want to maintain a particular temperature in the room. So we are taking air at this condition. We dehumidify this. So we pass it on the cooling coil, whose surface is at a temperature equal to the dew point temperature of the outside air. So what will happen? The excess moisture will leave this air. When this air is coming and striking this point, this is the dew point temperature, or this is the apparatus dew point. So at this point, the air will strike the surface, and excess quantity of moisture will decrease from the air. Now this air cannot be supplied to the room, because if you are supplying this air, now this is too cooled air. If you are supplying this air in the room, excess cooling or very chilling effect will be there to the occupant. So they will feel the discomfort. Then what we do? We heat it. First we have cooled it, dehumidified it, then we will have to heat it, and after heating, at some point we will supply this air in the room, and this air will take up the latent heat as well as the sensible heat load of the room. So here three processes are being done simultaneously, that is cooling, dehumidification, and reheat. अब ये कैसे करते हैं देखिए. हीटिंग, one more is situation is heating with humidification. Suppose we have to heat the air in the cold season, January, February, in the season of Rajasthan or Delhi. Suppose the outside temperature is very low. Once the temperature is very low, the humidity will be also low. So once the humidity is low, we have to increase the humidity. So for increasing the humidity, we have to inject water particle into the air. But air is at a very low temperature, so we cannot inject the water into the air, because at low temperature, the air may not absorb those water particles. So for that purpose, what we do? We put a heating coil. Over the heating coil, we are supplying the fresh air. Now this is heated up. Now once its drivable temperature has increased, now it can require extra moisture so that it can get humidified. So after heating, we are supplying this air on the humidifier. This is the humidifier. So यहाँ पर जब आप भेजेंगे इस air को, after the air passes on the humidifier, then its humidity will increase and that air will be supplied to the room. So this process is known as heating and humidification. This we do normally in the winter season. Evaporative cooling, this is done in evaporative cooling is done in desert cooler, and this is nothing but the same adiabatic humidification process which we have studied before. This is the same thing desert cooler में होता है. डिजर्ट कूलर में आप देखें यहाँ पर फैंस लगे हुए हैं और 3 साइड से आपका ये पैड्स लगा हुआ है और water tank is behind. There will be pump, so water will be dropping on this pads. Pad will be wet. From behind, from the 3 sides, the water is the air is sucked. Now this air will be coming in contact with this wet pad. So what will happen? Its temperature will fall down, the air temperature will fall down, and moisture content of the air will increase, and that air is supplied to the room where the cooling effect is to be generated. So here basically in the desert cooler, we are doing the humidification and cooling. Addition of moisture, सेम वही देखिए कोल्ड एयर है आपका, बाहर से हमने लिया, ये आपका डक्ट है. We are heating here in this section. This is the heating can will be here. So from here we are getting the warm air. Now warm air is passed to the humidifier. So humidifier में आप जो warm air को आप पास कराएंगे तो इसकी moisture content, the specific humidity will increase and some temperature will fall down here. Then further इसको हम heat करके फिर हम इसको further supply कर देते हैं desired space में. So this all process depend upon कि आपका लोकेशन कहाँ है, वहाँ का आउटसाइड का एनवायरमेंट कंडीशंस क्या है, इनसाइड का जो रूम कंडीशंस क्या मेंटेन करना चाहते हैं, उसके ऊपर आपको डिपेंड करता है. डिपेंडिंग अपॉन दोज पैरामीटर्स वी विल हैव टू डू द मल्टीपल प्रोसेसेस लाइक humidification, heating, sensible cooling and all. So these are this is all about the psychomatics. In case you have any question related to this topic, you may ask me. Otherwise, our session is up to this point. Hello.
Thank you so much, sir, for your enlightening training session. And I think we have finished with our stipulated topics for the day. Am I right, sir?
Yes, madam. Yes.
So I would request all the participants to kindly put up your queries on the YouTube chat box within next 2-3 minutes, so that we can also let the expert take a lunch break, because sir has not eaten anything since morning. So with this, please take 2 minutes for writing your questions on the chat box, and that will be placed to the expert. The teacher's training for skill course air conditioning and refrigeration was for today itself, and it will not be repeated for next coming few weeks. So if you have any queries, please do ask right now. Sir, would you like to say something in between, because we are also, wrapping up the training session. So I would like to thank you, sir, Mr. Pathak, sir, for taking out time and giving such a wonderful lecture on air conditioning and refrigeration. And in the meantime, I would just like to ask, if a student of CBSE school takes this course in class 11th and 12th, what are the future, prospects for the child?
As we know, India is a very developing country. Now we are moving towards, as per our Prime Minister, we will be developed country in near future. Taking that point of view, we see the living standard is increasing. Every house is having the refrigerator, desert cooler, air conditioners. Every malls, hospitals, everywhere you are finding these facilities. Now, once upon a time, it was luxurious. Now it is essential uh, component. So there is a wide scope for the students for repair and maintenance, design. So at whatever level the student is available, whether they are at the uh, ITI level, diploma holders or degree holders, depending upon they have the bright future in service sector in refrigeration and air conditioning.
Okay, okay.
So
So it is also that for higher education, you can always go to Delhi
higher,
State, an entrepreneurship university where they're offering courses at higher education level. Yes, sir.
yes, madam. We have at Delhi Skill and Entrepreneur University, we have here diploma level education and degree level educations.
Okay.
So students who are coming from 12th background with the vocational certificates, they are given direct admission in second year of diploma courses.
This is so wonderful. This is a technical subject, and I think every one of us who is watching it needs to spread it that if you are class 12th refrigeration and air conditioning course holder, certificate holder, then you will directly get into the second year of Delhi School Skill University rather
Second
than
year of second year in diploma studies. Once
diploma
you
study.
complete, in case you complete the diploma studies, then you will be directly joining the second year of the degree studies.
Oh, this is so such a good news, because
Yes, yes,
students can directly go on the second year of diploma and second year of degree courses after this.
yes,
So after
yes.
12, they cannot join degree course directly.
After 12th, they cannot join degree course directly on this vocational certificate. They have to do the diploma first.
Okay. So there must be
Or
other subjects that are being taught. So there has to be some sort of bridge linkage. So diploma course is kind of a bridge between the
yes,
degree and class 12. This is also a fantastic way of progressing in
this is for
education.
those students who are not brilliant much, those who have uh, of average students. So they can join the diploma courses first,
Hmm.
basis on the basis of this vocational course. Then after pursuing the diploma, 3 years diploma,
Hmm.
they can join the degree courses in the second year. So this is the
Okay.
added advantage for those students who are not brilliant.
Okay, that is a good news, and I think we do not have any questions on the chat box. So I would now thank Pathak sir for his time and his knowledge that he has brought on to this training session. And we have wonderful news from him also, that after 12th, the students can go for second year of diploma and then directly get into the second year of degree course. So this is a good news, and with this I am now signing off this training session. Thank you so much for all the participants who are being with us since morning, and please do fill the attendance link, and only those teachers who are teaching this course in the CBSE affiliated schools will get the certificates. So with this, thank you so much, Mr. Pathak, and we shall be meeting again for next training session. Thank you.
Thank you.